And Tom, I think it's 1 o'clock, so we can start the session if you are ready.
Just about getting ready. So let's see. Okay, so it's 1 o'clock. It's the 22nd of September, and I wish everyone welcome. So I guess it's good morning or good day or good afternoon or even good evening, depending on where you are. So as this is a virtual Nordic Systems Engineering Tour this year, we can welcome everyone from everywhere, which is kind of great. So let me just give a little bit of background. This event is a tour that was initiated back in 2013 as a smaller group of chapters here got together as, let's say, well, let's make an event where we actually bring a number of speakers to the local places. So rather than the participants having to travel far away, why don't we can get some really good international and national speakers at the local site. So the founding members of this was the chapters here presented. We have Finse, and then we have Rico Salmonen on board here now, who's handling all the Zoom stuff. So he's with us today. I was part of the Swedish chapter of founding members, but also Eric Herzog, who's with us, I guess, or may not be active today because he has other meetings at the same time. From Norway, which was the third chapter here, we have Cecilia Haskins today, who will be co-hosting together with me and Riku. And from INCOSE Denmark, we have both Henrik Baslev, who was part of the original group, and then Jens Christian Andersen, who's here with us today. And last but not least, we had the German chapter with the front figure of Tim Wilkins. And actually, we extended the borders of this Nordic in order also to include Poland. So we have had a tour that has been touring around in Helsinki, in Stockholm, in Linköping, in Oslo, in Copenhagen, in Hamburg, and in Warsaw. And this we've done a number of times. As of last year, we have done this now virtually. So while the Nordic countries is limited to only a subset of this, we, of course, in good INCOSE spirit, like to extend beyond sort of country borders. So let's say the Nordic region includes this, and now today the whole world. So welcome everyone. We have we would like to thank the sponsors for this as well. We have a number of companies that are pitching in here to support the chapters. In particular, also this year we have, of course, less cost doing this virtually, but we are also using these kind of support in order to do other events and publications, etc. So thank you. So with that start, I think we can get almost right to the important stuff for this of today. We have a number of presentations coming up here. We will have a little break about 20 to 3 o'clock Central European time. And then we have another 2 presentations after that break. And we will end with a little outline of what some of the activities that are happening now within INCOSE in the next near future. I've also invited a president-elect. As you may know, I'm one of the candidates, but also invited Ralph Hartman just to show our faces and urge you to vote. So that's a little end at the very end of this tour. So with that, don't know if there are any questions. If somebody has anything in the chat, please put your notes there. Otherwise, I think we can just get started with the first presentation. So Cecilia, are you online and able to introduce our first speaker? Maybe we were a bit.
Okay, the answer is I'm here, but I think we coordinated that I would be introducing the fourth speaker. I mean, I don't have his formal bio in front of me, so the best thing is to let Michael tell you the technical aspects of his career, but I can tell you that he's been a long-term member of INCOSE, and specifically of the INCOSE Israeli chapter, and he's also someone I consider a good friend and a superb colleague. So Michael, tell us a little bit about yourself when you begin.
So with that, Michael, do we want to take over the screen?
Yes, gladly. Thank you, Cecilia. Nice to hear you. This is very, I'm a little bit touched. I'm sorry. It's been many years of friendship and working together with many of the colleagues. So it's it's nice to hear it. I will use my presentation, and I will say a few words about myself using the presentation. So where can you please stop the screen sharing, Tom, so I can share? Thank you very much. Thank you very much. This wonderful technology we have with Zoom, so we can still have interactions. Okay, 1 second. It's just a little bit of. Do you see the presentation? Please.
Yes, we can see your presentation. Thank you.
Thank you very much. So I will tell you now. First, I am honored and delighted that my presentation has been accepted. And I am glad that I see so many friends in this wonderful audience you have for the NoSE tour. I have been talking to Eric about this, and when the tour was going on in person, we tried, and there were some things that didn't allow it. So now I am delighted to be here. So after Cecilia's question, I will tell you briefly, I have been in the systems engineering arena for several decades now. As you see in medical systems, I have been in, it doesn't say here, but I have been in the electric energy, large systems industry for 3 years as well. And then I went into aerospace, and in aerospace, I was blessed. I had the luck to participate in many very complex projects, and I learned a lot. And I was very glad that what I learned in university was to continue learning. So I continue learning all the time. INCOSE has been a wonderful background. Cecilia knows how many seminars we have been to continually update our knowledge and try to share. And in parallel with my passion for engineering in large systems, I had this commitment to teach. And you see now it's been almost 2 decades, and now I am extremely blessed and lucky that I am a full-time faculty member, and I have a group of systems engineering, and I have about 100 students in all for the MSc that are in my group. So I really enjoy what I do. Now to the presentation. The presentation is something that I am a little bit humbled, because many of the participants have been working on this and have a very vast knowledge. But since I say it's my passion, I say, okay, I will present what I have been doing lately on this issue, what is my present experience. So I will address the issue of model-based systems engineering application in industrial practice. And I will briefly go over of the vision that I have worked, as I said, in several projects. I've been lucky, I've been blessed to work in several projects with many of the participants. And what was the vision? What is still? But what is the reality we have to face? And I will want to share the latest work we have been doing and what, to my opinion, seems that is the promising directions in this area that we like so much and we have spent so much effort. I will warn you ahead that my statements in some part of the presentation may be controversial. So I will be glad to accept discussions and accept opinions that are contrary to what I present. And I even would be glad to share the results and the source code. I said this upfront, on the source code of the examples we're using for the research with anyone who will want to share and find a different angle, because this is all what the development in research is about, sharing and comparing ideas. So with that having said, the topics, I will go very briefly, just as I do generally, to have a common ground of what I present as embedded systems, IoT, and the focus of cyber physical. And then also very briefly, because I know that the audience is extremely conversant on it, on how it has developed in the last decades. And then I will plunge into what I see, what's the vision, what's the reality, and what are the examples we have been worked on, and how they seem to show a direction that I think is a good direction to continue. Now, embedded systems, I will not read it, you all know it. I just want to mention what I do, what I did in my work in engineering and what I do to my students. You have to take into account that they work because of the successful interaction between hardware and software. There is not one alone, not software alone, or not hardware alone. You know, if you would think about this fantasy that the computer will be only made of software, you will always find out that then you have the difficulties and the intricacies of hardware that get in the way. So, the interaction and correct work between software and hardware is what makes the success of embedded systems. Now, IoT, you all know, it's now being extensively used. I can tell you about 10 years ago, I participated in some European project in which they were trying to find what is the meaning and the applicability of IoT. They knew the word, and what they say is, what's the web of things? What is Internet of Things? And we even discussed things about what should be the meaning of the word. Now, that's all behind us. It's the interconnection of of many sensors and actuators with a net. Probably the internet in some industries, you know, and some organizations, it is using the internal net and not the internet, but the technology is the same, which allows now the joint work of many sensors and actuators in the control of something that many of you know for many years as was called SCADA, supervisory control and data acquisition, being an integral part. So now you have software, hardware, you have interconnection, some type of internet internal or the public internet, and some type of control, all working together to make the system work. And what we know, and I am thankful to my dear colleague, Professor Alberto Sangiovanni Vicentelli, that allows me to use this slide that he presented in some of the projects we did together, is cyber physical systems. So this is a visual of cyber physical systems, but the definition, if you look at the definition, cyber physical systems comprises the interaction between digital, the analog, the physical, the computer-based part, the software parts, and the human interacting with the systems, with their physics and their logics. And they are pervasive. They're all around us. They're ubiquitous. And the advances that we have in science engineering, in the case that I am talking about, allow us to make very complex systems, which in my present view should be all done for the social benefit of humanity. So we have to be able to take care, of course, of business efficiency, of operating efficiency, functionality, but not less reliability and safety. This is critical. You name it, collision avoidance in the present cars that we have with many functions that help the driver, or the vision of the completely autonomous transport, maybe cars, maybe in the heavy truck side, the train industry, all the robotic surgery, all that depends on health and the systems, sea exploration, the new ways of space exploration, and augmentation of human capabilities like virtual reality and so on. So here is the complexity of the systems, and I again remark the issue that what we should strive is also for business efficiency, correct functionality, but safety for the humans that are around these ubiquitous systems. Now, this classic, you all know, I guess many of you teach this. What is the issue of modeling? Modeling, the classics in engineering, prior to building complex systems, the engineer builds models. The abstract models are easier to handle. Being abstracts, you can present your ideas, you can present clearly your ideas, you can discuss them. But then one point is, this is the school I come from in the years I've been working, is that the accurate notation is what allows to verify the ability to meet the requirements, even the safety requirements. And this is the classic model of control, which uses a very well-defined mathematical language. And so what can you do with this classic control? We all know. One thing you can do is to observe what will be the result if you put it in simulation, in Simulink, or in a similar tool. You can observe the results. You can also analyze. You can analyze if it will be stable. Will it be unstable? This is perfect. This is before building. But also, as my dear Professor Preminger taught me, you can also design. You can use here the parameters, the K1 and the K2, to change the expected behavior. So using the models with a very formal mathematical language, this is for me the key of this model base that we are using. Using the models with the key, with the K1, K2, what my dear Professor Preminger used to tell me, listen, this is designed by analysis. You plan what you're going to do by using the mathematical modeling tools to analyze. So now we come to the computer-based, the cyber-physical systems. I'm sorry, it should be CPS, not CBS. I will correct when I send the PDF for everybody to be able to share. Applying model-based systems engineering will accelerate the process of developing robust, economic, safe. You can use all the adjectives that we were talking about. Cyber physical systems. Correct. This is the vision. So in the 70s, you all know the stories of the radars coming from Second World War, and then the development of the very large complex systems. So the functional idea, the basics for systems engineering. In the 80s, there was exponential progress in Europe, in the US. I had the privilege to be here in the time that Professor David Darrell was developing the ideas with the late Professor Pnueli in the Weizmann Institute, and the main author of the ideas is David Darrell, but there were authors around the world also pushing this exponential improvement. And there was an explosion in the modeling languages and capabilities that we can use to model this complex systems, and then to take advantage, like in all the engineering disciplines, of this issue of using abstract models, of analyzing the models ahead, of analyzing the properties, and before even building, even typing the first line of code or building the first breadboard for the electronics. For those interested, I can mention one reference which I like very much, is a real personal account of what we call state charts in the making, but it's much more than state charts. It's an account of what happened in the development of this method and the interaction between academia and industry. There are other, of course, you all know, closely following that, or even in slightly in parallel, we will not discuss the exact timing, is not relevant. We had the UML, you know, we all know about rational. Even today, IBM gives the proper name and calls it the rational set of tools that came with the UML, and the SysML derivative for systems engineering. You all know this, and the interaction between them. Professor Dov Dory led a very intensive project, and many people that are teaching around the world came out of this effort, even in MIT and the Technion, in OPM, which is another methodology for addressing the issue of model-based systems engineering. In Europe, in my humble view, a very successful effort in Modelica, some of the tools in the open arena, some of them in the commercial, of very good qualities with a very large libraries that can be used. So, and I had as I said, the good fortune to participate in large projects that were funded by the EC, for example, SPEEDS, in which the main idea is to reduce development time and cost for complex embedded systems. The complete name is while maintaining functional and safety and quality requirements. And you can see there was an effort that drove around many industries. Many of the friends I know that work there are still working in the systems development arena and still pushing these ideas around. So there was this great effort to make model-based systems engineering the leading tool in the development of systems. Okay, so one other aspect which in parallel develops, not in systems, in all the engineering disciplines, is computerized tools. Sometimes we call it CAD/CAM, but we call it model-based engineering, MBE, instead of MBSE, MBD, model-based design, variations on the same subject. But if you look today in academia or in industry, I think it is an indisputable truth, the statement that in electronics or electrical or in mechanical, the way to do things today is to use computer-based tools, modeling for the mechanical. There are many names, let's not go into it. In electronics, the students in the first, second year, they already start to use these tools, and that is the way it is done. In software, there is an interesting thing which I put here in the transparency in the slide, and then preparing in the research we are continuing now and preparing for the next semester that will start in October in Israel. I said, let's have a look. And I had a look at the recent things, September 2021, and something that was in the back of my mind. And then UML, what I see is that we have a question. Electrical engineering, no discussion. Mechanical engineering, no discussions. The one that deal with the physical artifacts, no discussion. Software, which is very culturally interrelated to systems, and where the development of models have been going in parallel for many years. Now there is some questions around it, which are being brought by academia around the world, and we'll see in a minute, and we'll see because I think the interaction between software modeling and system modeling for what we're talking, model-based systems engineering for complex cyber-physical systems is an important point. I would dare say a critical point that we have to look into if we want to see where we should be going. So I said, let's look at reality. Reality, 30 years, developing of tools, efforts in industry, in the applications industry, in the tools industry, in academia, courses around the world, across Europe, across America, India, Japan, China, you name it. South America, I've been with my colleagues in Argentina, in the center of Argentina, not even in Buenos Aires, and we discussed this with our colleagues. Colleagues from Uruguay, this little country I was born, come and we discuss the same ideas. Across the world, it's a well-known fact. You can look at the courses. I looked yesterday, one book being used by 175, one book on modeling being used by 175 institutions across the world. Okay, so no doubt about the effort and the courses I just said. But then I look at what I see in my environment, because I continue being in touch with my colleagues at the Israel Aerospace. And as I say, since I am in academia, now I have the good fortune to be able to observe commercial space industry. I am in touch with colleagues from Europe, so I get a view of the car industry and the newer developments. I get some, my children are now in the age that they are working in their own companies, so I get a view on medical systems and what I see. And as I say, if it's controversial, I would like to have your opinions, of course, is that the widespread of model-based systems engineering for complex cyber-physical systems as the leading instrument, as I would say, for electronics engineering is not taking off widely. The common situation still is there are many cases that they use drawing tools. They're very nice drawing tools. They draw in the board prints it, the board transfers it automatically to the file in the computer. But these are not model-based tools. Let's be frank about it. Okay, a drawing tool is not a model-based tool, not with a database, not with the relations, not with the simulation that it can do without a formal language, like this classical example I used about the feedback loop in control. And textual specifications. There are exceptions, I must admit. So I will put this up front. As I say, I will gladly accept the discussion to my points, but I will put this up front. Automated tools for managing textual requirements. They have been so efficient that in many places where 10 years ago we said, oh, you go to the tool and you do not write the specifications with a word processor, you write the specifications, the system shall respond in 10 seconds to the raising of the red flag and so on. Yes, I see commercial ones, an example is doors, but doors in their surroundings I have not being just, you know, the monopolistic tool vendor. Many other ones in many countries, they have it in their own language, extremely efficient. They put it like an editor in the screen. Every object is a requirement. They can trace it, they can say who owns it, and so on, and they can produce the documents automatically. Yes, these are not models. These are very intelligent text editing tools for presenting the requirement. And yes, there are showcase projects for complex systems that are being used. I understand from my friends in IBM that the last rover that is working splendidly in Mars was developed using model-based systems engineering. Yes, this is a very a project with high visibility, resources, with the support and the best academic efforts can be made there. And then complex components, as I said, in some of the complex components themselves, the brakes for autonomous flying vehicles, for UCVs, for vehicles with wings, not the rotary ones. Yes, for example, the models being translated into directly into the models. Okay, and I've seen in the car industries in Berlin. I have seen this robot that automatically sends pushes the aircraft from the landing site to the gate, back and forth. I've seen automatic systems that do nowadays alert the driver about difficulties being done with model-based systems. But as I say, this I see as the exceptional cases, not the common practice. For example, in Israel, it's common to say startup nation. There are many medium-sized industries that are doing systems. And continuously, they ask us to go and present. As I said, I have done this also in South America. I've done this with friends in Europe, where I have seen the same case. I confess I'm not in America, not in the US. Okay, and in those textual documents, no use of model-based systems engineering for the development of the systems. I want to point. These are the examples. For example, the example in CarMac or the example in Taxiboat that I just showed you, just to remind of some. And as I said, I heard from my colleagues in IBM that the rover in Mars was completely developed using MBSE. There is one point. So I said, look, so many years of work. This is a given? Is that something we have to accept and say, wait, if you can fight them, join them. We'll continue use ever nicer and more efficient textual presentations and drawings. I have many friends that say, forget it, this is the way. Why? We should not go, okay, we spend the effort and so on, but you know, if this is the general case and it's working, no, it's not working, but the issues of safety and then the issues of integration and testing that all of you know that take so much more effort and time if you don't do the models. Since I have the luxury of being in academia, I said, let's look at, is this a deadlock? Is this we have to wait? We have to say, let's teach other things. Let's teach artificial intelligence. Let's teach machine learning. Let's stick to the very new technologies that are also improving these systems and say, okay, it's not done with model-based systems engineering. And I looked at one specific case, which I think it's interesting to look. I said, fine. Okay. Man-machine interface of cyber physical modeling tools at least in general, or for the cases what I see there is antagonism in using them, is still they put on the table the issue that the interface is not like using the interface of a text editor, that those very efficient ones where you can write the requirements. There is a complex learning curve. What I was used to until, say, 4 years ago, 5 years ago, is you have to go to a 6-day course to be able to master a tool. And then I tell you the truth. I went to them. Even I went again and again to them. And then in academia, I said, what am I going to do? Am I going to give the students tools to use in the courses? Why I should waste 2 or 3 days of this? Do I have a requirement of doing first the, say, for example, the MATLAB simulating course? So this is another one. High complexity of the updating the model. This is the holy grail. What happens is in many projects they start, and when there are changes, and there will be changes, then changing the graphical models is a big effort, and it's not easy. And this is a breaker that they say, okay, they do the first round, and then when the changes come, they stop. So practitioners and management in the surroundings I see, not as I say in these fantastic exceptional cases and very successful ones, is that, wait, there is too much effort. We do not see the value of it. And I will add things that I've been seeing in the last year or two. One of them, because of the many cases that have been going to court, regulatory and certification demands are demanding ever more. I started in the 90s with this. We had to do specifications. I had to sign a 300-page document. Every page I had to sign to make sure to the contractor that I was certifying that all the requirements written in each page were correct. He didn't care about, I started already doing model-based. He didn't care. He wanted the signature. Now I see there is a revival. For example, medical, automotive, aerospace, the signatures. Then these wonderful text-driven tools do have the property that they let you rapidly move the documents around the world and control the signature process. So another one against. A widening cultural gap between software and systems model. Look, recently, this is this week, 2 issues this week. I had a very interesting interchange of emails and ideas with Professor Jordi Cabo from Catalonia. And I quoted what he put in his note this last Monday. UML is not the default option for modeling in software development. And textual modeling tools are blooming. And then there was this extreme discussion about the textual modeling tool is not a real correct term. There is no textual modeling tool, it's text. So the software people are doing text that can be automatically translated to models. So they first do the text. Now I think about the systems engineer I know about the students I know. They are not in this mindset. Their culture is doing drawings first. So they will use a drawing tool, not a systems tool. Agile software development values crafting about engineering. The leading authorities in this, Jacobson, Spence, Sidewitz, wrote this in 2016. You say 2016. The last seminar they had about this issue was this Monday. Bertrand Meyer, Jacobson, and other very respectful colleagues is if we can turn back the wheel, that agile software development has brought it back that the success is based on crafting, above engineering. So are we experiencing, or is there a widening rift between embedded, IoT, cyber physical, and the embedded software in it, and the enormous spectrum of professionals doing IT web-based software, where for them, this is the latest from this week, modeling is just not on. So I leave this question for discussion, and I want to use the last minutes I have to show you where I see we are going. Improvements in tool usability, agile MBSE, and something that comes from a similar area, digital twin. So in about a year ago, a year and a half ago, is where I said, can we get out of this deadlock? Can we do something? And we decided to make a research project. We just got System Composer from MathWorks, and we thought there will be available SysML v2 tools. I will make an open disclosure. There is no commercial interest invested. It's just the tools that were available for the research in academia. And SysML is only now coming with tools. So we said, let's look at this. And what we did is we compared System Composer using Exam, which you have the reference in the previous slides, which was used in many projects. I said, let's look again. The System Composer, I had to use 2019 version of MATLAB Simulink. Okay, so it's just recent. We wanted to do SysML v2. My open disclosure to all the presents is that presently I have a new team that is going to continue, and of course Visio, but you can use any open source drawing tool, and this is what my new team is going to do. We use Visio because it was available. It's just to exemplify a drawing tool. And then we use the two classical examples that I learned in the European projects from my colleague. One with very many, which means a system, monolithic system of high complexity, is a car damage monitoring system, and one of many of medium complexity. And since the light train in Tel Aviv has been in the news in Israel for many years and in the working, I said, let's do a simulation of these autonomous vehicles. It's not like the green ones. There will be one monocar, and they were running in many lines. So what is going? How can we model their behavior? And what I said at this, and I repeat, is we are willing to share the sources. The only requirement is that the results of any comparison that is done to our work is shared back with us. Completely open for any academic or colleagues research who want to compare. And we did a survey of systems engineers of what are the most important traits that they will want to see to compare the tools. And if you see visual convenience, updating the settings, this was done by my students, my students, Avi Saguri and Lior Mantin. They did the research among their colleagues. I have the situation is that our students, our MSc students are students that did not go directly from the first degree. There are students that have been working in industry for several years. So they have practical systems engineering ability. They could check with their colleagues. And you can see here 30% was given to making changes in the middle of the projects. There is an extensive paper which we are about to publish with all the details. And of course, when I present the paper, I can go back to the organizers, and whoever asks tells you where the paper is. And as I said, share the core with all the details, all the data, what we did, all the survey, who presented, what was the percentage and everything, okay? And what we saw, and the finding was As I said, this was research. We were seeing where are we going, and the finding was that using a computer-based tool with a known method resulted as the most effective for modeling. And now Lior and Avi say this is the only way to do. This is what they're doing in their enterprises. Okay, and I have further groups of students. And I will tell you another very interesting conclusion. Now, design by validation, I go quickly. I don't have to, you have it this in the PDF. Okay, you can model the system, you can model the components, you can model the behavior of the components, the behavior of the entire system. Now, the conclusions. So I want to close in 1 minute and leave it open for questions because of the timetable I have been assigned. One conclusion was there was no need for a special tool use course. I sent my MSc students on a searching trail. I said, you learn the tools by using the open tutorials in the internet. Lo and behold, with a little bit of support of Systematics, the local representative of MATLAB Simulink, with which we have an agreement of no commercial benefit to anyone, and everyone can use, they can use, and we can use, and I can share with academia all the examples that we did, is there was no need for a tool. I will give you the bottom line. This is what I do now in the projects. And I have seen, I looked into several projects again by chance from Catalonia, that they are doing the same. For example, for OCL tools, a very interesting paper I saw, OCL tools, a class of 140 students, and the lady professor that leads it said, we didn't spend any time, we sent the students to learn by themselves. I think they use Magic Draw, and another tool that is they had available, and it's very popular, and the students do it by themselves. The learning curve for my students disappear. I use it now in the courses. That's it. I use it in the course. The feedback I got at the end of the course, please give us more exercises with the tools for the future students. So the usability now seems to have jumped up again. I still, the answer from our research is that having one single environment for the tools. As I say, I do not endorse any tool vendor, but the single environment that was created by MATLAB Simulink and System Composer is very user-friendly. You do the entire system modeling, the physical components modeling, and the simulation in one tool. And object and simulation as the tool is the added value. In the thesis and in the paper, you can see through statement saying, look, in the middle of it, we found so many bugs with the simulation that we dumped the drawings with Visio. It was better to do it because we could do simulation up front. So agile, use light modeling, choose the views that you want to do. Do not go in this extensive, and I think, sorry for the word, sort of religious view that you have to have a book and you have to do everything that's in the method. No, you have to pick the views that you want, and then you have to do it formally, in earnest, in depth. Like the agile in software, but for modeling. Model, simulate, test, and correct from day one. Automatic software generation, I have done it. I have done it with my students as added value that you can feel in your hand, that you did the model, you did the simulation, you corrected. In the end, you can get VHDL, you can get C++, you can get Java out of the model itself and make savings in the process. A recent published book, as you see from March this year, is our dear friend Bruce Douglas, that puts these ideas in a extremely verbal and nice to read mode. The last one, digital twin. Digital twin is something NASA started in 2010, as a way to see that their systems were working properly. Now it's now at the forefront of systems engineering. I think together with Azad and Matt, okay, I present I took it from them, that the technology will be central in MBSE, will push forward back MBSE to the front, because you have to do the models and you have to do what I said here, continuous modeling, simulation, testing, and correction. So I presented the view of what I see here in my surroundings. And I also presented the view of what I think are very positive recent developments that will help bringing MBSE as a central tool for development of complex cyber-physical systems. I also presented this very intriguing idea of what is happening in the software arena for large software IT and web projects. There's a textual modeling tools, which I think we have to consider and look in depth, because this very deep interaction between software development and system development. Okay, I will be glad to have questions.
All right, Michael, it looks like you've generated at least a few good questions, and let's all first use reactions and send a virtual clapping to Michael for his very, very impressive and his very succinct and well stated presentation.
Thank you, Cecilia. How do you want to go about it?
Well, I'm not sure if you want to read chat. I was thinking I would try to like pick and choose maybe through the through what's in the chat, so you don't have to read and think at the same time.
Excellent.
Let me just see if I can get to where the questions are. So we got an early question about is there some kind of a solution that you would want to suggest to us about how we can get around this required signatures on documents? And have you seen any movement on that particular front?
Excellent question. Is something I will frankly invite anyone wanted to share research to do it. I've been scratching my head saying, okay, it is easy to have a textual documents signed. I don't think this signature document signing will go away. How can we do to have the models, to embed them, and to embed the correct version of the model between these very easy to use tools that can be signed, so that the model, once it is put, it's not tampered about, and the model, like, you know, the detail requirements for certification in the FAA can be done with Simulink in DO 178C, to embed them in the documents in a way that they cannot be tampered around, and the version is there. But this is just an idea. I will be delighted to share and to receive mails and to share research in this arena.
Super. Thanks so much, Michael. You also had some collaborating for the comments that you've given in your answer about the System Composer and Simulink has also been collaborated by some of the other information in the chat. Hopefully, Rico or Pekka, you're going to save the chat so we can share that with our speakers as well. And that first question was from Alexander. This next question is from Johan Tegler, and he's asking if you could do a brief elaboration about enterprise modeling vis-a-vis Archimate UAF versus an MBSE.
No, you mean enterprise architecture?
He didn't say that. He said, Johan, do you want to unmute and perhaps clarify your question for us, please?
Yes, thanks. I was thinking about the Archimate language or the general area of enterprise architecture?
Okay, I will tell you, the enterprise architecture I was aware of when I worked in Israel aerospace industries was more of modeling the process of the enterprise and the different ways we will do business. And there were tools that were more tools of a graphical type description without formal basis. So I did not dwell deeply. As I said, I would be glad to be exposed to tools that can do formal models of enterprise architecture to compare to these tools, or I say the key to having value is to have a formal language that can allow simulation. I know that some of the enterprise modeling tools can do simulation, but I humbly would like to have more information, and please, if you want to share it by mail.
Okay, and one question that I wonder if you would just answer through chat, because I'll ask you another question behind it, is whether you are able to provide us with some source information for ECSAM. There's some of us who aren't familiar with that.
Yes, of course. Yes. This is all public. This is all publicly available.
Okay, but just write it in. Just write it in chat so I can get to more questions that you could actually answer. There's a question in here from Aita. I'm probably saying the word wrong, so I'm sorry. Who has a question? She says, I might miss something, but what was the criteria measure of effectiveness in the research findings that you presented? You have mentioned the most effective things. Yeah.
The criteria, I think I am still sharing, as you can see, visual convenience was in the way if it was clear to see, to understand. Resetting is, for example, resetting the input. You have enormous amount of inputs. Updating the settings, you have to change the inputs, change inputs and outputs, change the structure of the components, moving elements around that do not destroy the entire drawing. You can see that in previous versions you moved around and you couldn't understand the result. A modeling language that is familiar to all project participants, of course, and the ones is that in the middle, for example, of modeling the light train in Tel Aviv, Lior had to change the model. He understood that the model was wrong. He understood, I discussed, I was the supervisor, and he said, oh, no, now I have to change the model. And that was a critical criteria of how much effort you have to put. And it looks that in the newer versions, this effort is much less. They keep the history and they allow you to make the changes in a graceful manner, let's say it that way.
I'm not sure. Tom, do we have time for one last question?
That's fine. Yeah, we can do one more.
Okay. This was an interesting one from Mats asking, how would you do agile acquisition in a cyber physical systems world?
Oh, nice question. Cecilia, you remember the times in the US, we discussed this about acquisition of the Department of Defense. Okay, so it brings many memories. I'll go back to the classics. If you are in the acquisition side, not in the developer side, my suggestion, my recommendation would be, from my experience, is that you deal only with performance-based requirements. I do not disagree with having a short list of which I call the critical or killer requirements. Do not overdo it. Do not go into the details of design. Do not try to specify what will be the software components. Do the performance requirements of what you have. See, the example is if I want to buy a car, and I am a little bit crazy about it, so I've done it. I didn't do a model. I did a short list of the requirements I needed. So how much miles per gallon should I have? How many kilometers between the maintenance period? Of course, the cost. Okay, so stick to the performance-based requirements. Do a list of what I call the killer requirements, that are the ones that are necessary, and then involve the acquirers together with the developers in the development of what I said, the common language of the model, where the discussion of the details will be done with a model that is commonly understood by all.
Okay, I'm going to need to stop you there,
Okay.
Michael. And I think, folks, you put your email in there, and I think folks with more questions, and there were a lot of good questions. And again, hopefully the chat is being captured and they can be shared with you, and you can reach out to some of the participants. Tom, I'm going to turn this back to you to proceed with the next speaker.
Thank you very much. Both, of course, Michelle, for a very interesting presentation, and thanks, Cecilia, for making that moderation of the Q&A. Okay, we're actually at the point in time where we will go on to the next presentation. This presentation will actually continue a bit on the topic of modeling, but in this case, we are looking at cybersecurity, the security aspect, which is of course becoming more and more of a concern for us in basically all stages of the life cycle. So I'd like to welcome Orsolya Nemeth and Salome Wagner from Sparks and Konrad Wieland from Liebe Software. Are you there? And ready?
Yes, hello. Yes, hello. Can you hear me okay?
We can hear you very okay.
Hello. Hi, it's Orsolya speaking. Salome is with me. Konrad is not here today, but I will do the presentation, and I'm happy to be here. And I would just start sharing.
Yep.
Let's see.
I think it's
Okay.
coming up.
One more minute. I'm on it.
Good.
That's the second one. Okay.
So,
And okay, so you should be seeing black screen with some funny colors on the bottom right corner. Is that right?
Oh, sorry, not yet.
not yet.
And now?
Still not, I think, Rico.
Yeah, let's see that we don't have any. I should have closed the previous presentations.
Yes.
So it should be open for you. So if you just
I just try to do it again, and then okay.
yeah,
How
I
about
think now it's working. Yeah, I think it was there was
Okay.
still one of the last presentation was there when you tried, so it doesn't allow two presentations at the same time. So I was a bit slow, sorry.
No problem. All good. Thank you very much. Hello and welcome. As already said, so what is this talk about? One thing, threat analysis is, of course, like an integral part of system development and still relies on subject expert judgment. So ThreatGet, you will learn what ThreatGet is, helps you actually to innovate these expensive and subjective processes by actually automating the analysis and, of course, formalizing threat information. So this is my talk. This will answer the question, why does cybersecurity threat modeling actually keep your organization innovative and, of course, how does secure IoT design actually looks like if it comes to ThreatGATT, of course. Before we go ahead, first of all, like a short agenda, I just separated this presentation in 7 parts pretty much, and it will be a brief introduction about what I do, what my company do, what we do with Austrian Institute of Technology. The second part is what is ThreatGATT, and then some of you might heard about that, the STRIDE framework. So I will explain the STRIDE framework, and the next would be then about the different ways. So how did systems development look like from pretty easy to understand to IoT. And of course, fifth one is IoT security situation. So some regulations, and of course, like some laws from the US and UK. So I will also cover that part so that you really have like a really good overview about what I'm talking about and what's going on as well. And of course, innovation, security by design with threat modeling. And last but not least, the conclusion of all of this. Okay, so go ahead. So this is me. I'm the speaker. I'm here with Salome, as I said, and I'm trainer, consultant, and speaker for Spark Services Central Europe and Liber. And also very important to me, I'm a co-founder of the special interest group, Women in ICT. So where are we? What are we doing? Some of you might heard about us. We're Spark Systems and Spark Services. Spark Systems headquarter is in Australia, and we've got sisters and services companies like pretty much everywhere on the globe. And then again, Liber Software is actually making or developing extensions for Spark Systems Enterprise Architect. But I will go ahead and tell you more about it. So here you go. Who we are. So Liber Software is, what do we do? So we have actually decades of experience in developing custom models. So we're really, we've got some expertise on model-based systems engineering. So with our product, that's Lemon Tree and Embedded Engineer, we offer extensions for, as I said, Enterprise Architect, especially in the model-based systems engineering. And this means that we also, so very important thing is like modeling infrastructure, because any company's established IT infrastructure can be adapted for efficient modeling. And of course, modern IT solutions utilize data or originating from many sources. So what we do is an integration enterprise architect with other tools. So that's what we're doing. That's on one hand. And on the other hand, we are working together with the Austrian Institute of Technology, which has got some key infrastructure issues, and that's Austria's largest research and technology organization. And AIT is also partnered to industry and public institutions. So Liber has got the tool pretty much, and Austrian Institute of Technology are our experts for not only, but in this case for cybersecurity experts. And if you bring together great minds, then a nice product, I would say, it comes out. So, and this is, as you can see on top right-hand corner, that's ThreatGATT. And it's a cybersecurity modeling with methodology. So ThreatGATT is a tool based on Spark Systems Enterprise Architect that helps in the design phase of many projects to search for potential threats. We're talking about different in automotive, but also in critical infrastructure, industrial IoT environments, as well as in railways. So, systematic analysis of designs is very important because it uncovers vulnerabilities and of course, including traceability and decision making. So that's what it is about. Before I go ahead and tell you what the threat get or how the solution looks like, I would like to go and to tell you a little bit of this STRIDE model. So, the STRIDE threat model. So that's pretty much a framework of security risks development, STRIDE, as you can see. When you're considering threats, it is actually always useful to have some questions or ask some questions. For instance, how can an attacker change the authentication data? That would be the spoofing part here. And sorry, it's German, but it doesn't matter. I will tell you what's in here. And of course, another thing is, what is the impact if you have an attack, if you have an attacker, and what can the attacker read of the user? So that's some questions. You can group threats into actually categories, and they really help you to formulate these kind of pointed questions. So that's why this threat model, this STRIDE threat model actually was developed, because it gives you more information, which part of the system and what part of the system and how it affects the system. So if you take a look at the first part is spoofing identity. I won't go and explain you the whole one, but I just want to get out the first two, like spoofing and tampering, what this is about. So spoofing means spoofing identity in this case. That's an example of identity spoofing, is illegally accessing and then of course using users' authentication information like username and passwords and so on. And tampering is like meaning that tampering with data. Data tampering involves the malicious modification of data, for instance. And the last one I would like to, for instance, elevation of privilege. So in this type of threat, an unprivileged user gains privilege access and thereby has, of course, sufficient access to compromise or even destroy like really entire systems. And so this is really a great model, and that really helps a lot. And that brings me to the next part, is like, how did like systems actually develop? At the beginning, there was the STRIDE threat model, but also at the beginning, the system or a system looked like this. So actually not too long ago, a system consisted of a user here, then of course an application and a database. The so-called trust boundary, so that's of course this one, was clearly defined and covered only the application and the database. So you could see that it was really over, you could see where the data, where information was exchanged from application to database and from application to user. So this was easy to see where there could be some threats entering the system or the trust boundary, if you want to. The trust boundary is a term for computer science and security boundary, actually to describe where program data or executions change their level. So here, of course, the trust level, so to say. And yeah, so of course, systems developed over time. And so what is the issue here? What is the system in the example? So that's, as you can see, it already says here in the middle, that's a cell phone, that's a mobile phone. with the advent of mobile devices and systems became a bit like, of course, more complex because you had different networks and apps. And we had to think about actually how to protect those systems from actually malicious users. Like, for example, by bypassing the mobile client and so on. So you can see that here right now, you've got the transboundary mobile device in the middle with your mobile application and malicious mobile application if you want to. And here's the data. And then again, a second boundary enterprise network with some enterprise web services. And here you've got some users as well. So this is the second step that's the system developed. And of course, also this, yeah, and that's the third one. That's how it looks like pretty much right now, maybe even bigger. But last but not least, with the IoT, the cybersecurity hype was that was very important. Cybersecurity became even on cybersecurity was really super focused, and it was very interesting to everybody because the system got so complex that it was hard to see right away where the entry points were for cyber threats. And of course, the concept of threat modeling is you first define the scope, what threat model you want to use, and then of course create your data flow diagram. And that's a typical process. Then you identify security risks, identify security control. That would be actually the next step, and countermeasures and mitigate risks and remediate threats. So that's how the process would actually look like. You really have to have an idea how you want to protect different systems interacting with each other. Okay, so this leads me to the next part of the presentation. It's IoT, the IoT security situation pretty much now. I just put in some information and what are the challenges today. This slide shows you that from 2010, 2018, so the attacks were 6 times higher. And also on the right slide, on the right part of the, you can see that there's a physical and remote attack. And in 2020, more than 50% of incidents were attacks by black hat hackers. So that's one thing. And I've got also some examples for you about, it's from 2020. What happened in January 2020? So some of you might know, or of you know, 4,000 vehicles were stolen in India with electronic devices. And of course, that allowed the thieves to control the module, to unlock the vehicle, and to start the engine and access the vehicle computer. And the next one was also in January, a Mobileye 630 Pro, pulled the ADAS of a Tesla Model X, and the autopilot system triggered the brakes. And of course, yeah, and steered it onto traffic. So this is another thing which happened. In February, it goes on, 90 security vulnerabilities were found in Mercedes-Benz E-Class, and this allowed hackers to remotely control the vehicle. In April, another thing happened. This time, hackers took full control over an OEM's corporate network by reverse engineering. And in August, and that brings me to the last example, a hacker or somebody managed to gain control of Tesla's entire connected car fleet by exploiting a vulnerability in the OEM server-side mechanism, and so on and so forth. And more than 200 vulnerabilities found, over 40 accused, developed by Tier 1 companies. So that's just some facts. And so that's why it was, there's the next point is, what about the legal standardizations and regulations worldwide? So in the US, the California Consumer Privacy Act was introduced. It's about it's a state level privacy law. I can give you the information, the link afterwards. You can ask me, no problem. So that's what it was introduced pretty soon. And then the Developing and Growing the Internet of Things Act was introduced. That's a national strategy for the IoT in the US. And of course, I think I've seen it today, I'm not sure, the NIST, the National Institute of Standards and Technology, has created a privacy framework with the volume 1.0. The UK Department for Digital Culture, Media and Sport introduced security requirements for all IoT devices, and the European Union did the following. ENISA, I think that was it, EU Cybersecurity Agency, published a study with the title Essential Security Recommendations for IoT in the Context of Critical Information Structure. So this information I've got from different magazines. You can look them up if you need more information on that. As I said, I can share the link afterwards. So the UNEC World Forum for Harmonization of Vehicle Regulations, World Package 29 defines requirements for type approvals, meaning that the members are of this type approval authorities and certification bodies, of course, who are affected, and OEM and Tier 1. And so there were new regulations, and on one hand, it was about cybersecurity, and the other one is about software updates. If we take a look at the UNECE WP29 regulatory on cybersecurity, what does it mean that vehicle manufacturers and also service providers and suppliers, they need to have a cybersecurity management system? And so it should cover development, production, and post-production. And this means the management of cybersecurity in the whole organization. This affects also management of risk related to vehicles. So the automotive, of course, not only management of new cyber threats and vulnerabilities. And on the right side, that's just an abstract of that. So that's to give you a short update, what's going on, how the regulations are. And the next part will be, okay, so how does that look like? How does innovation through threat modeling look like? I'm talking about security by if you think back, it looked something like that. What you need is you have to have a structured process. You have to check system of threats. So back in the days, there was a Bailey, a wooden keep, and a mod, and so on. That's how a village, for instance, was protected. And well, of course, there were some bad people, some bad people who wanted to attack the village. So this means that you have to have a systematic approach. And of course, that's about vulnerabilities and threats. And of course, people learned and started to build bigger systems, bigger castles. And here the structured process is to check system for threats. I'm talking about how threat modeling works. You fix the identified problem, of course, and then you build a bigger, in this case, on the left side, you build inner walls and outer wall. You've got towers, inner towers and outer towers. And you can see that even here, people learned how to protect themselves from threats which were coming outside the walls. And on the right side is that systematic approach, vulnerabilities and threats. And the next thing is that, of course, also on the left side, as I said, the castle to be protected. On the right side, people who want to destroy it. And very important is, if you take a look at the systematic approach, it's the vulnerabilities and threats. And what you have to do, you have to update vulnerabilities and threats. And so it was always updated. So you can see that there was like really some innovation going on, who got better and so on. But today it doesn't look like this anymore. We're talking about computer system. We're talking about IoT, digitalization. And so that's what I want to show you. That's in Enterprise Architecture, that's already ThreatGet. ThreatGet is a add-in, so it is built on the Enterprise Architect platform. And sorry, this figure shows actually the data flow between like different internal units in, this is a vehicle. So you can see the radar and the camera and the radar. Units which, of course, collect data from the external environment. These are then processed by the sensor data fusion and decision-making methods. So here you are, that's right here. And again, the data is transmitted to a telematics. So that goes on here. And that controls the tracking pretty much of the vehicle. And the telematics, again, interacts with the central vehicle control. So this is then here again. And to control the speed of the vehicle, of course, either by brakes or like to by acceleration, doesn't matter. The infotainment connects to the telematics unit, of course, to provide information to the driver, and so on and so forth. So that's just to see how this is connected, how this design, how this model looks like. And that brings me to the other slide. So if you take a look at this slide, what does ThreatGet actually do here? ThreatGet scans all elements and connectors. Just go back a little bit. It really scans all connectors and all the elements here in the model, and then it identifies the potential threats. On the right side, you can see like a threat list. In this example, you can see that it's 46 potential threats. So they're detected, of course. And ThreatGet then, of course, summarizes all detected threats in a user phase. This interface has the following meaning. So that's the threat list. So that's here pretty much. You've got here, that's why I wanted to show you the stride method. You've got here the type of the threat, that's spoofing, repudiation, information disclosure, and so on. And right here, you've got the description, and you even see the impact. Is it the major? Is it moderate? Is it trivial, etc.? And on the very right side, you can see the likelihood. So it's really likely, and so on and so forth. So a screenshot image of the source of the detected threats severity, this evaluates the dangerousness of the detected threats, actually, to determine like both impact and likelihood based on these parameters translated. So it even shows you here, is it like the severity, is it medium, low, and so on. Good. And here, the next thing is that ThreatGet performs a risk assessment in order to calculate the risk. And these risk levels can be assigned with the ThreatGet risk matrix that's here. So that's trivia, you can see, that's the impact, likelihood. So that's the second, that's minor, and it's remote. And again, here you've got the likelihood is very unlikely, that's green. And if it's like, you know, towards yellow, then it's possible, and so on and so forth. So this is low, medium, high, and extreme. I think you've got that. This gives actually, so for the first time, it is now possible to consider safety and security requirements already in the design phase of a system. So this gives European companies a considerable market edge in this increasingly important field, actually, of practice. So here you go again. That's a system model. I just summarized now. We've got here the systems model, and then you've got here a toolbox, a kind of toolbox with in the back end, and there is the security properties, which says access control, administration, and so on, and it says whether it's defined or undefined. And what you can do is to model your system, and of course, what it does an automated analysis, and that's what I showed you before. That's the found threat with impact. So that's a really whole list you get from that. And the other thing is that you have down here. So right now it's 48 threats, of course. Cybersecurity risks asset, and you've got here the category, it's tempering, the severity is 5, and yes, as also see in the list, you've got here some description, and you can also write down some notes. So this is really a risk management support as well. Okay, so what does it mean? So what is the conclusion of this? This is a ThreatGet for automotive. I just talk about the ISO 21434. ThreatGet gives you a threat catalog. It's UNECE conform, also ISO conform, and it uses the IET analysis. And what it does, if there are new threats, it automatically updates the whole system, the whole catalog. And of course, it's ISO compatible. It's an ISO compatible workflow. What you can do, you've got some like risk analysis. And with that, you can also generate like or create like a reporting. And very important is that it's really also extensible by users who are, of course, allowed to extend it if it's necessary. If it, you know. Good. This is pretty much, I think, my last slide. So, as I said, security by design means. So ThreatGet has this automated security analysis of design. And of course, it avoidance of vulnerabilities and insecure architecture. And it supports systems design risk analysis, as I said before, ISO. And then, of course, the compliance with ISO it just becomes mandatory. So, and knows current and future threats. So there is a threat database update, and ThreatGuide updates the threat database regularly, meaning that it's easy verification of systems already, actually on the market. Yes, and I hope that I could give you a short overview about security by design, and we're happy to take your questions now.
Very good. Thank you so much. And if I could ask everyone again to put a clapping hands reaction out to thank Orsolya for her very excellent presentation. At the moment, we're sitting with a first question, but I suspect others will arrive quickly. This one's an interesting one. How are the CIA security properties linked to the impacts? Did you hear me?
Yes, again, sorry. Mm-hmm. Could you repeat it? Mm-hmm.
How are the CIA security properties linked to the impacts? Unfortunately, I really can't read the name because it's written in a language I don't speak. Did the person asking this question wish to come on, unmute and ask the question directly?
Yeah, that was me, Stefan Marvidel from Airbus, Germany. So an impact is always linked to the loss of one of the CIA properties. So a threat is not simply a threat. A threat is only a threat if you clearly state what the impact in terms of loss of the CIA properties are. This is how we conduct our risk assessments.
Oh, yes. Okay. Yeah, here. Mm-hmm.
So just stating a spoofing threat is definitely not sufficient.
I think they're looking for a reaction from you as to, you know, they also asked the following question as to why you did not elaborate on threat scenarios.
Yeah, so the threat scenarios from our perspective are the most important thing to do, because if you have, let's say, a particular threat at an interface, which you classify concerning the strike methodology, that doesn't give you anything about the danger, I would say, that the system is exposed to, because we're always looking at the end-to-end functionality.
Yes.
And
yes,
not at a single function, because it's only important if you connect it all. And that was not clearly stated in your presentation at all. So I have an interface, an external interface, which is a threat vector, and then I have a threat path to a target. And this is what I have to assess. And Stride helps me, definitely, but I need to see the threat scenarios.
Yes, I see. Yes, I got you. So the thing is that if you what you do is you really look at the whole architecture you put into to the model, and so that's why I mean I just brought the Stride method because it's just a short brief introduction, but you really look at the whole architecture of the system, and that's where it actually shows you and gives you the information on the threats entering the system. And of course it could be like more. It could be like how should I say? There could be like more or 2 or 3 threats which are entering in the same space and affecting your architecture. But you actually look really at the whole architecture in the model, and you see it actually right away, and you click on it. And what ThreatGuide does, it just gives you the information. Is it actually even endangered or not? So yeah.
Yeah, I was a bit missing, because you talked about security by design. I was a bit missing how you came to the design step then. So typically you start top down, but then, and this is what the model is supposed to give you, you do the functional breakdown. And when you arrive, let's say, at a lower level, you then say, okay, I add a security measure here. Let's say I implement an authentication function, and that reduces my previously identified risk by X points.
Yes.
So what will give that? What will result? What will be the resulting threat potential if I add that particular security measure, and so on and so forth? Yeah. So I think that this is something I would really like to show you in the model itself, like in Enterprise Architect, because that's really something. It's easier to answer if I'm in the model and I can show you how this is done. Yeah.
Okay. So I'm unfortunately, according to our schedule, I need to stop the Q&A. There's one or two questions still in the chat. Maybe you can look and answer those individually. And in the meantime, I'll say thank you. And Tom, I don't know if you want to say any words before we break.
Well, let me just share the screen, so I'll put that on while everyone's away. So let's see. So it's time for a 20-minute, well, it's at least 18 minutes of a break now. So why don't you take the opportunity maybe to chat with somebody individually? You can, look in the chat window and maybe you find some old friends or some new friends. And then just, you can chat with them directly if you choose that name, right? So, and for the rest of us, maybe another little coffee break or something. And then we see each other at 3 o'clock for Niels Jørgen Strøm. Very good. So till then, have a good break.
Could we, with Niels, could we check that Niels Jørgen, your audio is correct and we can get your slides?
Yeah, hi.
Yeah.
Can you hear and see me?
You. Yes, thank you.
Okay, good. So everything is okay for that then. Thanks.
Hello, this is Dave Walden. I just want to check my audio too while we got the break. Does it sound okay?
Sounds
yes,
great.
Thank you.
All right, thank you.
Good to see you.
Nice to see you as well.
Okay, I think we are almost there to be able to continue. So, Tom, are you already online? Yes.
I'm online and alive. So, very, very good. We are 3 o'clock. So I think it's time to get going with the next presentation. And for this, we would like to introduce, let's see if I can just move my little arrow here. Here we go. So Niels Jørgen Strøm from Grundfos going to talk about how they can use systems engineering to be more effective, to look at how they can create more effective pump solutions. It was very interesting to read the little introduction that pumps around the world almost count for 10% of the energy consumption. So tell us more about that, Niels. That sounds like a real challenge and a real opportunity.
Yes, thank you. I'll just share my screen. So, can you see my screen?
Indeed.
Yes.
Yeah. I hope it's the blue one with the title.
Yes.
Correct.
Okay, good. So, and now also sharing my video, I hope.
Yeah, we see.
Good. Yeah, so thank you. Welcome, everybody. Thank you to the committee for inviting me. I'm honored to be here. And thank you to all of you for staying on to listen to me. We are all on individual journeys, in our individual companies. But don't believe no two companies are the same. We try to serve our customers in the best possible way. But even so, we are all different. Even though we are all different and stand in different situations and circumstances, I really hope that what I can tell you today will serve as inspiration for your own situation. Because the purpose of my talk today is to share with you how the embracing of systems engineering at our company has really fueled our change agenda, and has done so on many different levels, actually, across the organization and through times of change, both in competition, in organization, and ways of working. My name, as just being said, is Niels Jørgen Strøm. I have a background as an electronics engineer. I've been working with product development for, I think it's almost 40 years now. Today, I'm a chief software architect in the embedded software development unit of Grundfos. I've been with Grundfos since 1996, and I held many different positions dealing with systems engineering and processes within both software, hardware, mechatronics, and the background in systems engineering is that I have an SE Cert Level B certification. So the agenda for my talk will be a little bit about Grundfos, why we engage in systems engineering and what it took to do so, how we use it to simplify and improve our process landscape, and then I'll end my talk by providing an overview of some of the achievements we did. Yeah, you may know Grundfos at least by name. We are a global company. We have approximately 20,000 employees worldwide. Our headquarters is in Denmark, and we have a yearly turnover in 2020 of 3.7 billion euro. We manufacture pumps and pump systems, and as I said, I'll give you a short introduction to serve as a base of understanding why systems engineering is relevant to us. It's our goal, and we take pride in moving water to where it should be. Our products and systems provide remote areas with water. We remove water when there's too much of it, and we also treat water when it's polluted. And we want to do it using as little energy as possible. Every year, we produce approximately 16 million pump units. This also means that we have a huge impact, both on the water agenda and the energy agenda, and a lot of people are affected by our products every day. We have a strategy that is linked to the Sustainable Development Goals of the UN, and they serve as a global guideline for us. So let's take a look at the water story first. As I think we all know, the world is facing a water crisis, and climate changes doesn't make it better. We see more floods, and in other places we see droughts, and both are getting worse. It's just one example is then that still more than 500 million people are still without access to clean drinking water. So what we do is to help our customers providing sustainable water solutions, such as treating wastewater, distribute water in better ways, and also providing access to clean drinking water. And coming back to the impact, these are some examples on how many people are actually in touch with our solutions. And from these examples alone, you can see in total almost 1 billion people daily. And then a little commercial related to the water crisis. Amazon Prime recently added this movie to their selection. It's telling a true story about what happens when water becomes a scarce resource, when water even becomes an object to crime. So maybe, just maybe, the Friday night movie experience you've been looking for is right here. And then turning to the energy efficient part. Pumps are used for many, many applications. And therefore, even though many people might not think of it, as was just being said in the introduction, pumps currently account for minimum 10% of the world's total electricity consumption. That's a lot. And by switching to energy efficient pumps, we can actually cut that down by 50% and then save 5% of the total consumption. That's quite a lot, and it has a potential for a positive impact on the climate. The reason for this huge potential is not only that that new motor technology is much more energy efficient, because that's of course a part of it, but it's also that pumps often run at much higher speeds than needed because flow demand varies. So if pumps and motors adapt to the demand and only provides exactly what is needed in the system, we can potentially save half. So depending on the application, what is needed will vary over the course of the day, over the course of the season, and human activity. And if pumps are running only when required, that will also relate to the water story and has a big systems aspect built in. So think about high water pressure in freshwater systems. If we have high water pressure at all times, we have increased loss of fresh water. We have strain on the piping systems because in some cases they are a bit worn and they may be damaged by high pressure all the time when there's no demand. So also here it's important. Yeah, so sorry about that. Yeah, this example that comes on now shows what has happened to the area of small circulator pumps from 1999 until now with regards to energy consumption. As you can see, the newest domestic circulator is using less than 20% of the energy compared to 1999. As an example from my own house is from 1997. I actually had a pump like that on the left top corner there. It used 30 watts all the time, and in 2021 I now have one that uses between 3 and 5 watts. Sorry, somebody is talking.
Go ahead. It was somebody who was unmuted. Okay.
So the pump I have in my house now uses 3 to 5 watts. That's most of the time, sometimes a little bit more. So actually you have these 17% in the energy consumption compared to when the house was built. So why systems engineering? Well, I think we are all on the wave of the fourth industrial revolution, and especially in the last few years, connectivity and digitalization, bringing not only new business models, but also new services to the customers, something we didn't think about 15 years ago. But also bringing with it the technical complexity that we have to control. This drawing comes from a Harvard Business Review article written by Porter and Hebbelman. It is called How Smart Connected Products Are Transforming Competition. As you can see, it's about agriculture, but it's actually pretty generic in nature. And I would, you should read it. It's a really good article. So we try to look at it from our perspective, putting pumps in there. And even though a tractor or a pump in their own right are actually rather complex systems, then, you know, with more products being connected to other systems, with digitalization as an enabler for creating the services to the customers, with enabling of software sales and software updates, and also with an increasing security threat, as we just saw in the previous presentation, technical complexity increases manifold. And we had to find a way to cope with this complexity, bringing the organization closer together to create better collaboration. And early on, both in Grundfos and in other companies, I have very often experienced language problems. Not in the usual sense, you know, when we talk about language from Chinese, Indian, German, or English to Danish in my case, but rather between production lingo, mechanics lingo, hydraulics lingo, electronics, software, and all other kinds of lingo that you find in a company. So we often misunderstood each other. We often didn't even know we were misunderstanding each other. And sometimes it was causing rework. Sometimes we simply just wasted our time. And not just because of the lingo, but also the way of thinking was different. There was no common reference. So what we found is that systems engineering provides both a common lingo and a common way of thinking about systems. So it becomes natural for everybody to talk about models and simulation before physical prototypes. It becomes natural to think in alternatives before deciding for a particular solution, and to distinguish clearly between problem and solution. And today, everybody knows about the system hierarchy, that everything should be treated as a system, even if you think it isn't. That you have a system of interest, that you have enabling systems, cooperating systems, and so on. That some systems are even not defined per se, but they are still there, and that emergent behavior from such systems is a risk to observe. And that's, as I heard a clever guy say at some point, you should always look up, down, out, and around your system of interest to recognize the system hierarchy and take it into account. So we decided to go for systems engineering according to the INCOSE Systems Handbook, with the underlying ISO 15288 standard as a foundation. And the really great thing about ISO 15288 is that it doesn't care about how you execute, agile, non-agile, doesn't matter. And it describes a set of connected processes that are free of professional boundary specialities. What did it take to embrace it then in a professional way? In the past, we have had many improvement initiatives. They have often been driven by grassroots, and that certainly has its advantages. But this time, we really wanted the entire organization to be buying into this, so we decided to run from the top. So management has been leading the way by visibly promoting the need and make funds available for professional education. That has provided us with the opportunity and the possibility to involve all disciplines, ranging from fluid mechanics to embedded software, as well as our manufacturing engineering division, working together across all of these boundaries and offering it also as an opportunity for personal development with an official certification for those colleagues that are interested in that. So within the recent 5 years, we have therefore offered the training. We have had a bit of a setback due to Corona, obviously, but we now have approximately 30 level B certified systems engineers, more than 100 basically trained systems engineers, but the numbers are growing all the time, and managers at all levels support the initiative. And we decided to use an external company to do the training to make sure that it would be professional and according to international standards. We still do, and we are very satisfied with it. It is really worth the money. The training is carried out with mixed classes from different parts of the organization, also to create that network. And we have included many case exercises based on the Grundfos world, as well as reflections about today's practice in Grundfos. The highest level of training we offer is on level B with an official certification according to the German NoSE chapter certification scheme, where there are 3 steps from level C to level A. Level B is a 15 days training in 5 modules, and you have to make a reading and self-study in between. It's finalized by an exam, which is both a multiple choice exam and an open case-based questions, which, if passed, gives you the level B certificate. And actually, on top of that, you get a complimentary CSEP certification. It's quite a hard exam, but it really motivates the studying. And then we also have the basic training, which is a 6 days course without official certification, but with a small exam at the end to check the learning. And on top of this, we have internal training within particular areas, which means that we are reaching a large number of colleagues, and the word is really spreading fast. And as you'll see a little later, we have, for example, a modularization course based on systems engineering, and we have a systems engineering learning portal with, for instance, ISO 15288 process learning. So, for instance, just as a small example, no project is started today without a system boundary definition drawing in the same format for all projects. And in general, systems engineering terms and work products are on the way, becoming an integrated part of the workflows and processes that we follow. We also created an internal and cross-organizational community for everybody who went through the training or who would have similar knowledge from elsewhere, to maintain the cross-organizational network of system thinkers, to keep up with the systems engineering skills, to work with and develop relevant areas within systems engineering, and of course also to share experience and knowledge. And as you can see there to the bottom left, we had a voting among all of these systems engineers what would be interesting to work with. So we have a working group within MBSE, for instance. We have a working group within requirements management and so on. So we work all the time to improve. This is our systems engineering learning portal. It's open to everyone. It offers different kinds of systems engineering related learning topics and small quizzes to check your own learning. But still, the basics of the learning is the classroom education that I talked about before. With this knowledge, we have chosen to simplify our process landscape and the workflows, describing how we execute. We have, let's dig a little bit into the process landscape. For many years, we have been process-oriented. So we are an ISO 9001 audited company. We have for many years been in good control of our processes from top to bottom, and we also have internal audit and assessment programs. But over the years, the process landscape has become increasingly complex, especially because we have established life cycle processes in different professional areas. So for instance, a hardware architecture process, a software architecture process, and so on. And it's because originally back in the late 90s, we created a set of software processes, which were the first area that we really, worked with. And we built them on what is today known as ISO 15504. And we then expanded this to create our own individual process reference models for hardware mechanics and so on. And that gave us a large number of processes. We were in control, but sometimes it has been hard to maintain a holistic overview. And on top of this, we wanted our workflows and processes to be much better connected to our portfolio model in order to create an end-to-end view that connects better to the business needs. And this model we call idea to market. It covers the entire value stream from group strategy to the phasing out, the end of life of manufactured products and systems. It's not a sequential model. All the phases or elements of the model take, so to speak, place at the same time. Everything takes place iteratively in cycles of different pace. And to support the elements of the model, we have created workflows that in a simple and clear manner describes how we want to work and what should come out of it. And then each of the workflows connect, and they connect to the 15288 processes, and only to those. And this means that here's an example of how we've been able to reduce the number of processes in our process landscape by replacing individual processes with one ISO 15288 process. So in average, maybe a 3 or 4 to 1 ratio. So for instance, we have now one architecture process. It makes it much more natural to look at architecture as one holistic approach, following the same architectural principles across the disciplines. Of course, there are still discipline differences, but they are then captured in the workflows. What have we achieved? What has been influenced and improved by systems engineering in the past 5 years? Yeah, I'd like to give you an overview of the most important things and then dive a little bit deeper into one of them, namely platform and modularization. And an example of an important that is an example of an important strategic initiative we have. It has a huge potential for cost and time savings, and is really heavily supported by systems engineering. So today we have a critical mass of educated and certified systems engineers. We have created a systems engineering community of practice, robust against organizational changes. We have a process landscape which has been simplified and aligned with ISO 15288. And we are working with systems engineering improvement areas, such as, for instance, requirements management practices. And around modeling, yeah, for many years, many years, models and simulation have been a completely natural part of our hydraulics design. But in other areas, it hasn't. And the systems engineering has really, opened everybody's eyes to the strength of models and simulation in all areas. So that is being heavily improved. And we are also partners of a research collaboration called Chalmers Software Center. I don't know if you know it. It's founded in Gothenburg, Sweden, but it's international. And that research collaboration also has a systems engineering part. And with the knowledge we gained, we are able to participate in that part also and to push the INCOSE agenda there, together with companies such as Volvo, Ericsson, Tetra Pak, Saab. And then finally, as an overview, and that's the one I want to dive a little bit into, we have the platforms, architecture, and modularization part, which has really, that was the one I said that was the important strategic initiative because it has a huge savings potential. So as an introduction to that, I'm going to push my luck a little bit and see if I can play a little video. And for that, I need to share also system sound. And I know this is maybe a little bit dangerous, but I'll try anyway. If you cannot hear the sound, don't worry. There is also a transcription on the video, but it's of course better with sound. So let's try.
Modularization in Grundfos. Here we have a Grundfos factory producing pumps. Looking across the landscape, we see several such factories and R&D sites working to deliver high-quality pump solutions to our customers. Let's take a closer look at some of our products. In Grundfos, we have pumps for many different applications and performance levels, efficiently produced across a global network of factories. Looking across the pumps and factories allows us to see commonalities and identify opportunities for improvement. In our modularization efforts, we focus on one module at a time. If we, for example, look at a specific module, we often see a number of different design principles. When we look across the program, this adds up to a wide range of different solutions. If we take a closer look and add some cost and performance data, we see that some designs perform well compared to cost, while others are expensive compared to the delivered performance. The question is, do we really need all these different solutions? Look and add some cost and performance data, we see that some designs perform well compared to cost, while others are expensive compared to the delivered performance. The question is, do we really need all these different solutions? So here they are. From a market perspective, we would like to offer a wide range of options to secure maximum customer satisfaction. From an R&D perspective, we always have new, innovative solutions. From an operations perspective, we want minimal complexity to maximize our manufacturing efficiency. We know we want to optimize our common business. The challenge is to find out how. In Grundfos, we want to work dedicated and focused with this challenge until the optimal trade-off between standardization and number of modules have been found. We strive to find the optimal set of modules to cover the needed performance in Grundfos and to minimize overlap. We document these as standard modules in the module book so that we can use these optimal designs as a reference for future solutions. As we start to apply the modules, we will gradually see an increase in commonality across our pumps and factories. This is driven by both redesign and by integrating modules into new designs. We define standard modules only because they are key for our success. Some modules we have because they are critical cost drivers, others because they are essential for quality, and again others because they are key for our time to market. Finally, modularization will enable us to innovate and differentiate our products and services for future market requirements. This is how and why we work with modularization in Grundfos.
Yeah, I said I pushed my luck. Obviously, that was true. I hope you could see it anyway when I restarted it.
Absolutely, Niels Jørgen, and that was very, very motivating. I'm assuming that was how you were closing?
No, unfortunately not. I have a few more things, if that is okay.
Okay, you're just going to cut into your Q&A, but yeah, if it's important.
Yeah. So let me share again. Yeah, sorry about that hiccup. That's when you take a chance. Sometimes you don't have luck. So systems engineering really helped making this effort as broadly understood as possible. So communication between engineers with a very diverse background and with very different fields of work has become so much easier by using the common background of systems engineering. So to aid platform development and to make it easier for any developer to find and reuse elements, we created what we call the Grundfos Design Library. And that was actually what was called the module book in the video. We since then, we changed the name to Grundfos Design Library. We are embedding reference architectures in there. We are embedding system elements for those reference architectures, and not only for the products, but also for production. So there is a link between the two. So you know which production elements can produce the product elements. And that has a huge savings potential because production systems are so expensive. This is a great screenshot from the library showing a single element and how it relates. This is another one for the same element showing information such as where it is used, how mature it is, who's responsible, and so on. And you can then find also the link to the production element that's able to produce it. So we decided to create what has become a very popular internal course as well for modular architectures with participants from all professions. As you can see here, it introduces or offers some recaps on systems engineering and then proceeds onto the concept of modularization. And then came Corona. We couldn't make classroom education, so we decided to make it virtual. So now it's part of our systems engineering learning portal. And this is the content of one of the introductory lessons for that virtual course now. As you can see, you have this short introduction of systems engineering concepts and language. And here, some specific content explaining we're using the RFLP architecture methodology. We have chosen that because it really very much facilitates modular designs. So what you see here is, for instance, functional breakdown, N2 diagram. You see IBDs, internal block diagrams. You see physical architecture, and also a mapping between functional breakdown, logical architecture, and physical architecture. So that's really becoming widely used, and that helps in promoting this initiative about modularity and platform. So coming to a conclusion now, I believe we can say that embracing systems engineering has been a big success for us. Not that we don't have challenges in everyday life, because we have, of course, but it has brought our company much closer together with this common language, a better ability to collaborate, an approach to cope with complexity as well, and a common base to stand on. So this was what I wanted to show. I hope that part of it may serve as inspiration for your journey. If your challenges resemble any of ours and you're looking for ways to cope with them, you may be able to apply some of it for your own change agenda, and maybe achieve some of the same benefits as we did. Thank you.
Okay, very good. Thank you. And then let's all thank Niels Jørgen with a quick reaction, clapping of hands. Okay, I think you've not left us too much time, so there's some very good questions.
Sorry about that.
Oh, that's all right. Let me start with one that I think perhaps everyone shares. How long ago did Grundfos start this journey toward the implementations of systems engineering, as you've described?
That was in 2016, 15, 16.
Okay, and then kind of a complementary question that's come up from multiple sources in the chat was related to the motivation for your top management to actually begin this initiative, and then also how they're measuring the return on investment, or how they're measuring what they consider the success. Is it just a gut feeling, or do they actually have some measures?
Yeah, it's hard to say what is the result of an improvement, or what is the cause of an improvement, right? You can see the improvement, but what was the cause? And I think the motivation for management to go into this was that management really recognized this huge complexity rise, right? That complexity would rise a lot, and that we would probably, if we did not do anything, we would see an increase in market falls because of emergent behavior, and we would see things go wrong because we simply lost the overview of the system. So we have a measure in place measuring an alert system, you could say a market alert system, where we really we follow closely up on released products. and that measure has increased or has improved considerably during the last 5 years, actually. So the question is that because of this, or is it because of something else, or also because of something else? I think everybody can see in everyday life that engineers collaborate more across the professional boundaries. They have it's more easy for them to do so, and that products and systems are increasingly being created in the same way across projects, and it also makes it easier for engineers to move around in the organization. So I think we have this market fault measure, which has really increased. I'm not saying that we had a lot of faults on the market, but we often caught them before, and it was expensive to deal with them, and we have much less now. So I think quality-wise, we have really seen an improvement.
Well, that's really fantastic. Thank you for such a complete answer. A secondary question that's come up was I feel that the training you talked about certainly focused on the training that the different engineering disciplines receive. The question is related to what sort of training do your project managers or product managers receive? Is it the same or something a little bit different?
It's the same. So we actually pull everybody through the same courses. So whether it's the level B, which we typically give to those that are really the ones that need to have the big overview and have this holistic view of the projects. And then everybody who's going to work in a project needs to know, and they need to know it. They need to have this basic training of the 6 days. So project managers also receive the same training. Yeah.
Okay, very good. We've got a question in here again from Johan Tegler. And Johan, I'm really sorry that I always have trouble understanding your questions, but I wonder if you wouldn't mind coming on and asking your question about the connection between IT and OT systems, please.
Yes, I will try. Do you have connection between the process systems like QualiWare or management systems and the operational system like CAD, PLM systems?
I'm not sure I understand fully. So do you mean quality assurance tools connected to the CAD systems, for instance?
I mean, when you're supposed to follow a process,
Yes.
and that you have your development tool like a CAD tool, then
Yes.
you need some guidance and checklists. And
Yeah.
if they are
Yeah, true.
connected into the CAD tool, it's more convenient
Yeah.
compared to if they are
Sure.
in a separate handbook.
Yeah, sure. It is in a separate one. We have a system where we have created these workflows, and these are actually the ones that people use in everyday life, but they're not connected to the CAD tools, for instance. That would be very, very nice. And we have also a group working with preparation for PLM, but we don't have PLM right now. Would very much like to have, but it's also something that you should really plan with care, because it can end up in a total disaster if you don't plan that carefully. So we have process management systems, like we have somewhere where we model all our processes. We have a tool for that, and we have the workflows connecting to that, but that, as we speak now, not connected to the CAD systems, unfortunately, not yet.
Thanks for the answer.
Maybe the next logical follow-on to that, Niels Jørgen, is whether the company has a thought to go in that direction or not.
Yeah, we have, and it's of course also related to the discussion about model-based systems engineering, because we have parts of it is model-based. So we have feature modeling, for instance, and feature models connected to modeled requirements in NoSE NG. So they connect and they create a platform of requirements that you can configure actually. So you can reuse requirements. We have of course the CAD systems, which is modeling in themselves, and we have been looking into if we or how we should connect all of that, because you know, really to go for full MBSE means that if you have an object, you have it only once, and then you can view it from different angles, and that's not where we are today, but we are looking into it. Yes.
Yeah, excellent, very good. And I suspect your modularization approaches will be very helpful for that. Well, we are actually, we are out of time now, so if we can ask you to stop sharing so that our next speaker, who is David Walden, can come in and get his slides set up. And while we're waiting for Dave to set his slide set, I can do a brief introduction of Dave Walden for everybody. You can see here on the screen, his topic is key skills for moving beyond Greenfield systems engineering. So it's probably talking a little bit about what we as systems engineers deal with more on a daily basis versus the way we often teach it in academia. So Dave Walden is also an ESEP, so he has the highest level of INCOSE professional certification at this time. Professionally, and David, could you be starting to share your screen, please? So you're ready to go as soon as I'm done talking, please.
I can't share yet, so whenever I'm
come on, Tom, get off the channel here. Thank you. So David has a professionally rich background, which includes more than a decade with General Dynamics and with McDonnell Aircraft each. And in terms of his contributions within the INCOSE community, he is currently and has been for some years our, thanks David, our lead editor for our INCOSE handbook, which is the basis upon which we award certification. He is also our INCOSE liaison to the ISO technical committee on SC7, and he's part of 2 separate working groups in that capacity. And he served as our first certification program manager from 2007 to 2013. From the perspective of education, you can see that at the bottom, the man has 3 master's degrees. For heaven's sakes, David, I didn't even know that about you. And he's got a Bachelor of Science in Electrical Engineering as well. So without further ado, if you are ready to go, even though we're a few seconds early, I think you can start, David. Thank you.
Thanks, yes. And for those of you that know my wife, some of you from INCOSE, she says no more masters. The 3 is the limit, apparently. I wanted to start with just an interesting thing. I'm coming to you from beautiful Valparaiso, Indiana, in the United States. But I think as we get more older or seasoned, we get more concerned about the past. So I've been diving into genealogy, and I do have some Nordic roots. So I'm just going to show this. The top half is my wife is pretty much 100% German. So her main name was Handrock, and they're based out of Naumburg, Germany. But from my perspective, I'm a mix of things. So, but my paternal great grandfather came over as a Walden and changed to Walden from Vage in I cannot pronounce this. I should be able to, but Prestegild or something in Norway. And I have other relations on my maternal side that came from, my paternal grandmother came from Kristiansand in Norway. And I've got another great grandmother that came somewhere in Norway, and we don't know yet. So my son and I are gonna catch up with Cecilia and Terje and explore some of that. But also have some, northern Germany, and now that you've expanded to Poland, what was Prussia at the time when they came over. So I think it's interesting how all these flows, and that's when they cross the big pond to come over to the United States, and their journey to get me and my wife to here is where I'm coming from right now, is right at the southern part of Lake Michigan near Chicago, is Valparaiso, Indiana. So I just thought that might be interesting, just so even though I'm coming from the United States, I do have some Nordic heritage in my blood. So, but to get to the point of the talk today, what I want to talk about, and I appreciate the opportunity to talk with all of you, but I want to talk about some key skills for moving beyond Greenfield system engineering. I'll introduce what these terms are. But we see that the abstract that I put out is that it's my contention that system engineering practitioners do a lot of work beyond how system engineering is typically documented. What I call this document-centric Greenfield, which means you could say clean sheet of paper or blank sheet of paper system engineering as we move forward to tackle the complexities of the future. So we're going to talk about what I mean by Greenfield and beyond Greenfield. And we're going to talk about some hard skills. The hard skills are more the engineering or technical skills, and the soft skills that you need to succeed. And just as a background on what I mean by soft skills, in case you're not familiar with that term, there's a lot of different terms. Some people find the term soft skills, disparaging or degrading because they don't give them importance. They're not hard, they're soft. But what they're meant is the term is that these are the interpersonal skills, the people skills, the relationship skills that we need as humans, but particularly as system engineers to do our job effectively. You can see some of the other names that it goes by. If we look at the INCOSE competency framework, we can see I'm sure you all have this, by your nightstand. But on page 28, you can see some of the professional competencies that are listed in this one. Communications, ethics and professionalism, technical leadership, negotiation, team dynamics, facilitation, emotional intelligence, coaching and mentoring. Those are some of the soft skills, or what they call professional competencies, that are identified in this. And we just want to emphasize hard skills, which are important. Things like doing requirements engineering is an important soft skill. Architecture, important. Verification, validation, doing trade-off studies. These are all important hard skills that we need, but what are some additional soft skills that we need as well as the hard skills? One thing I want to emphasize is these pictures of these beautiful dogs is that the little puppy up on the upper left, he's reading about how to swim. Okay, so I don't know if any of you have read that book on how to swim lately, but you're sitting at the side of the pool and you're reading a book on how to swim. You're not going to be able to know how to swim by reading a book on swimming. You got to be like that dog on the right. You got to jump in. You got to jump into the pool. Soft skills are the same thing. I'm going to give you some introduction to soft skills, and you can read about soft skills all you want. But if you want to be a better communicator, if you want to be a better leader, you need to jump into the pool. You need to try these things. You need to get out there maybe even in a safe environment, or have trusted people give you feedback while you're doing it, so you can jump in the pool and try these. You're not going to get better at soft skills in particular by reading a book on them. Okay? You got to jump in the pool. So be like that black lab that's jumping in the pool and try these things to get better at them if that's something that you need to work on. So with that basic introduction, I want to first start with at least my definition of what I mean by Greenfield, or what I call traditional system engineering. I use the acronym TSE, but traditional systems engineering. We've had some people talk about this now. Keep in mind that, as Cecilia said, I'm the lead editor of the greatest handbook ever. Okay, says the lead editor. So take everything I say about the handbook with a grain of salt. But even as the lead editor, I would say, as was mentioned in the previous situation, the handbook is fairly neutral on how you apply it. But if you would just read it without a lot of background, you would interpret it, I think, as a kind of a greenfield or clean sheet or blank sheet type of approach. We assume that you're going to make a lot of the things instead of buy them. We assume primarily a single pass, but you could do it with that. We do emphasize that all of the processes are done concurrently. There's iteration within the same hierarchical level, and it's recursively applied, tailored as appropriate at each level of your system hierarchy. So we've got this concurrency, iteration, and recursion. But again, if you look at it, we show it's primarily single pass. We also, again, we have model-based system engineering in here, but we have it a document-centric view with requirements as the source of truth yet. Now we're moving to the model-based, where the model becomes the source of truth. We also tend to emphasize, again, we've got product lines in there, but the product lines are shown as an approach to do this, where we have a It usually has a single product instead of a product line focus. The product line is an adaptation of this. And we usually approach it from a complicated versus complex versus system of system or Internet of Things type of approach. Again, those are ways we would tailor the fundamental processes. And of course, social considerations are important. We have, you need to consider all of your stakeholders from a social perspective and regulatory compliance. We have human factors, but they're considered important, but it's not like a social system. That's another tailoring of this. And this is reflected, I think, in both the handbook and the ISO standard. It's not a criticism of it. It's just, I think you could read it that way, that you would start from a blank sheet of paper. And I'll emphasize that with one of the things we like to use as system engineers is the V, right? And people love or hate the V. And we're going to get into that philosophical discussion. There was a nice panel session on that at the latest NoSE International Symposium. But the way that you read a V, the primary flow is you start at the top left and you go down the left-hand side of the V, typically called system definition. And then at the bottom is where you either implement it if you're going to make it or buy it or reuse it, but then or else you would, as was said in the previous discussion, you'd recursively apply this at level n+1, n+2, till you get down to those atomic nodes where you have enough detail where you can make it, buy it, or reuse it. Then, of course, we need to bring those things back together in integration. You go up the right-hand side, bottom and right-hand side of the V is usually called system realization, where we integrate, verify, validate, and transition. And what comes in are a set of needs from your stakeholders, technology, get a certain amount of money, you have a certain tolerance for risk. You might be a very aggressive firm, market leader. You might be very risk averse, very safety critical environment. And what comes out is not your documentation, but your actual system of interest at whatever level you happen to be. And this can be entered at any level of your system hierarchy too. So now again, we emphasize that all of these things are going on concurrently. They're going on in parallel. You don't wait until the end to do validation. You think about it up front. The V nicely shows these horizontal relationships between validation and your stakeholder requirements, between verification and your system requirements, between integration and your architecture, particularly your interfaces. And then, of course, at the bottom, when you get down to that make buy, you've got your hardware, software, people, procedural aspects, services aspects, whatever the nature of your system of interest is. And we show that it's iterative, it's easy to show. And this is trying to emphasize the recursive nature, that we recursively apply this. So it's not this simple, serial model, but it can be interpreted as that. But when we teach it, I'm sure many of you that have been to classes, we start with our business or mission analysis. And we say, do we understand our stakeholder needs and requirements definition? Can we translate that from the voice of the stakeholders and the voice of engineering for system requirements? Then we architect and design our system solution. We do system analysis as necessary, implement it, or recursively apply this again, integrate it, verify it, validate it, transition it into its operational environment. So it's kind of implies this serial process, but we recognize again the concurrent, iterative, and hierarchical nature of this process. But this is the baseline for what I mean by the Greenfield traditional systems engineering approach. It's a good approach. I'm not disparaging it, but we often have to tailor it for the different environments that we're in. When we look to a traditional systems engineering approach, I use some analogies here, and these analogies are just to get you to think about things from a different perspective. These are not the only analogies you could use, and then there are others that you might find more useful. But when we're in a traditional make type of a systems engineering environment, I think of the craftsman as, I think of the system engineer as a craftsman. If you think about a musical analogy, the person that makes that beautiful Stradivarius violin, they understand all the nuances of the wood, the strings, the bow, how they come together. So using that analogy as a traditional system engineer, we try to first understand what the customer's needs are, translate those into requirements, stakeholder requirements, system requirements, and then we try to architect and design a system solution, and then further allocate and derive those requirements into system element requirements at level n+1, n+2, and so on. And of course, we are verifying and validating continually the solution. We don't wait until the end. We can verify and validate our requirements. We can verify and validate our architecture and design, as well as verifying and validating our realized solution. So this is how I'm defining traditional system engineering, and we've created great systems with this process. My contention is some of the key hard skills that we need as traditional systems engineers. One is that we need to be able to do requirements analysis. That's a critical hard skill that we need to have, and we need to know how to architect and design a system solution. We also need to know how to bring the pieces together in integration and do verification and validation. We need to understand how to do decision management, how to do trade-off studies. We need to understand risk management as a key hard skill. So I'm categorizing those as hard skills. Another key thing we need to have and that we leverage as traditional system engineers are what we call the ILIDs. People love or hate the term ILIDs too. We call them ILIDs. Sorry, maybe mute someone, please. But we call them ILIDs because most, but not all of them, end in ILTY: affordability, reliability, usability, producibility, sustainability. Some don't, like safety, and the second presentation talked about a very important ILID, security, right? Where we look at threats and how they can compromise our system. But these ILIDs let us look at the life cycle considerations and think about the end at the beginning. So these are just, again, some of the baseline hard skills that every system engineer has, and these don't go away in these other applications. Some of the key soft skills that I feel we need to have as traditional system engineers is, one of them is communication. If we cannot communicate to other people, we are not going to be as successful as we could be as system engineers. We need to be able to ask questions. We need to know what to ask and when to ask. We need to surface contradictions and things like that. We also need to have the soft skill of teamwork. System engineering is not an individual sport. System engineering is a team sport. If you are doing system engineering by yourself, you are not doing system engineering correctly. And we also need to have some cultural understanding, both our internal culture and the external cultures that we deal with, our customers, our suppliers, our teammates. So we need to understand culture as a traditional system engineer. So with this baseline, as this is what I mean by Greenfield traditional system engineering, let's talk about moving beyond system engineering. You can see the four that I'm going to cover, but if we go back to that slide of traditional system engineering is typically characterized by these things, in the interest of time, they asked me to keep this to 30 minutes. So I'm not going to cover COTS, Agile, and model-based system engineering. Those are other ways that we tailor and adjust system engineering. I'm going to focus on, I thought the ones that were most relevant would be brownfield system engineering, where you don't start with this clean sheet of paper. That's not the assumption. You have a legacy system that you start from, and you go from this as-is system to a to-be system. You don't start from scratch. This is common practice in a lot of industries. I think with the automotive industry, the model, it's very rare that they create a clean sheet new paper. They have new model years, and every 3 years they might do a major refresh, but they're still starting with an automobile. The next one we're going to cover really follows greatly from the Grundfos presentation that just happened, is going from this single product focus that gives you a lot of different variants to this product centers focus. And that leads to what we call product line engineering. So we're going to talk about how we adapt and what are the new hard and soft skills for product line engineering. If we move from the complicated, not easy systems, they're still complicated systems, to what in NCOSE we call complex systems, that leads us to what's called system of systems engineering, where each of the constituent system elements is a system in its own right, and we need to manage the emergent property of the overall system of systems. And we also are going to talk about where social considerations are important but ancillary. We're going to move to a socio-technical system where social considerations are primary, and we think about the human and technical aspects of the system together. So these are the ones we're going to go beyond traditional system engineering. Just in the interest of time, I'm sorry we can't cover COTS, Agile, and MBSE. You can invite me back again for another time to cover those if you'd like. So let's talk about brownfield, or also known as legacy systems engineering. We use these terms, brownfield, greenfield, and brownfield. They come from real estate development. Usually greenfield is you're out there in Finland, north of Helsinki, there's a farmer's field, and your new company wants to put a new tech center out in this farmer's field. That's a green field. That's what they call that. It's this nice green field. You can do whatever you want in a greenfield development within regulation, of course. You still got to follow all your regulations. But you can put the roads where you want. You can put the utilities, the sewer, the gas, the water can go where they want. You can use those great pumps to pump it all over the place. You've got, within regulations, you can't do whatever you want, but you can do it within regulations. You can have a lot of freedom here. Whereas in the other case, let's say you're in downtown Helsinki and there's this old factory that's been abandoned since the 1970s or 80s, and you want to put your new tech center on this location in downtown Helsinki. Well, that's a brownfield development. There's existing structures in place. There's the utilities are where the utilities are. Here's where the water main comes in. Here is where the gas comes in. Those are additional constraints in a brownfield environment that you don't necessarily have in a greenfield environment. The other key thing about brownfield, you can see here, is this factory has a lot of waste that might need to be cleaned up before you can use it. So this is where the terms greenfield and brownfield come from, in case you're not familiar with that. If we apply that to systems engineering, greenfield is no or very limited legacy system constraints, other than the system interfaces and, and regulatory constraints. We still have to deal with those. And another key aspect is no or very limited continuity considerations. There's not an as-is system that either needs to keep running and be modified or totally replaced without disruption of operations. You think of a subway system like the tube in London. When they added in the new, was the Crossrail, the new Victoria line, they couldn't shut down the tube for 12 years while they did that. The tube had to keep running while they add additional capability. This is also sometimes known as clean sheet or blank sheet systems engineering. When we move to brownfield system engineering, this is where we have a legacy system. We have an as-is system. And the job here is to either do a significant modification, a new extension, add new capabilities, or a total replacement of this existing system in its existing environment. The three main reasons we do this is to maintain it, to modernize it, or totally replace the system. Usually there are explicit continuity requirements, like that tube example that I gave you. Usually, or not usually, but typically, there's also a significant amount of waste. In engineering, we call that technical debt. There might also be some technical debt, some waste that needs to be cleaned up before you can move from that as-is to the to-be systems. Things that were deferred, things that were decided poorly. A bunch of spaghetti code that needs to maybe be refactored or something like that. So there's also this waste or debt. This is also known as legacy or in-service systems engineering. One thing that I'm proposing, so again, take this with a large grain of salt. This is a sysnovation model where I extend the V to account for some of the key brownfield activities. I make the V look like an N, where the V you can see look like the letter V. This looks like the English letter N, right? So what we add for the N, and you can still see the same V is here, but what we add for the end is we add this site survey that needs to be done up front. And the way you read the N is you go up this reconstruction leg, down the definition leg, and up the realization leg. Now, again, remember that there is concurrency, there's iteration, and and recursion that's going on with this as well with the N, just like with the V. But the idea here is, depending upon what as-is system you get in, you reconstruct. If you're giving nothing, if you're not the original developer of the system, you get it from some other company, at least you have the as-is system. You can look at it. You can then you might have to first identify what the elements are. That's system element reconstruction. You might actually have to infer what the architecture and design was at. That's architecture and design reconstruction. And you might then have to, if you don't have requirements, you might have to reconstruct what the system requirements and ultimately what the stakeholder requirements are. And then we use those again. There's a relationship between the stakeholder reconstruction. You're doing it parallel with the new stakeholder requirements, needs and requirements definition. You're doing system requirements reconstruction in parallel with this, in parallel with verification. I should even go all the way over here. You're doing architecture reconstruction in parallel with architecture definition, design definition, and planning for integration. And of course, implementation corresponds to element reconstruction. So this is just, again, take this with a grain of salt, but what comes in here is the as-is system. You still have the new needs for the to-be system, any new technology, dollars, and risks that you have, and you're doing, again, this concurrently iteratively and recursively throughout your system development. And what comes out is the to-be system. So this is, again, a way to characterize a brownfield development. So the analogy that I use for this is the archaeologist. Think of your favorite archaeologist. You know, Indiana Jones is a popular movie series in the United States, right? He's out there. It's not always as exciting as Indiana Jones, but they're out there with their brush. They're trying to study the past to design the future. That's what I believe that the brownfield system engineer, it's a little different hat. You're envisioning the move from this as is to the to-be system. So some of the additional hard skills, again, none of those traditional system engineering hard or soft skills go away, but some additional hard skills you need to have is this ability to do a site survey. You need to be able to look at the as-is system and say, this is what we've got. Then you need to be able to reconstruct that as-is system moving forward. An important additional hard skill you need to have is a gap analysis. You need to understand what's the gap between what you reconstructed and what you need. So you can then identify that transition to go from as is to be. Some additional soft skills that you need in a brownfield environment. You need to be able to investigate things. You need to be able to go in there and figure out what's going on. You also need to be inquisition. You need to determine what's real in that. You need to look at the legacy documentation and say, what's right here? You need to be able to have a lot of discernment. There's going to be a lot of people coming in with a lot of different ideas. You need to discern what's real and what's not, what's right and what's wrong. And you also have a cultural aspect, but it's a little different culture here. This is the culture between the legacy team, especially if you created the legacy system, and the new development team. There's going to be different cultures there. The legacy team will have a lot of history, which is good, but they'll also have a lot of baggage, which may not be good. The new team will come with a lot of new ideas, which is good, but they won't understand the challenges that have already been explored, which is bad. So you need to understand this legacy and new system culture as well. So that's how we change our perspectives for brownfield. When we go to product line engineering, that video that we just saw was an excellent example of this, right? Product line engineering is looking at it from a business perspective and saying, how can we make a set of pieces? I use another great Nordic company here, right? Legos, right? Legos. So this is a great example of how you can make lots of different things from this. But our idea here is to leverage product lines to make our business operations more successful and our customers more satisfied. So here's another great Nordic company, Volvo, right? I just got this off of your website. There's a lot of different variants. If we just look at anything, you know, skid steers, look at all those different models. I am guessing that Volvo does not make, how many are there? 2, 4, 6, 8 or 9 of those. I'm just reading it real quick here. Let's say there's 8 different skid steer loaders. I'm confident that Volvo doesn't have 8 different architectures for skid steers. They should have a product line architecture that embraces the bigger set of this, and then they have different instances that they produce. Now, if there's fundamentally different sizes, they might, things like that. But even across these different platforms, there's going to be some opportunities for commonality. So what's the best architecture to produce all these different variants that your marketplace is either expecting or demanding? That's where we go into product line engineering. There's a new ISO standard, ISO 26580, that came out with feature-based product line engineering. It came out in this year, so it's a hot off the press standard. But the idea with product line engineering, feature-based product line engineering, is we still follow the V and we create this set of shared assets that we have, supersets. Sometimes you'll hear in product line engineering the 125% architecture, the 150% architecture. Then we need to create a feature catalog simultaneously. This is all done concurrently, by the way, too. But we have this set of features. These are the different variants and variant points and options that are allowed. And then we need to come up with a bill of features which says, for these different offerings, here's the 8 different type of skid steer loaders. These are the allowable combinations of features. If you think about it from an automobile perspective, a Volvo automobile, they've got the low, the medium, and the high end of these automobiles that come out. Well, again, certain combinations. Maybe you only get the sunroof with the high end. Maybe you only get the certain navigation features or certain things. The low end only has cloth seats available instead of leather. So there's certain features that are only allowed in certain combinations. That's what your bill of features portfolio comes up with. And then you use the PLE factory to say, all right, let's understand these features, and we've got the assets, the shared assets. How do we pull those together to create the instances of these different product assets? These would be the different, this is what the customer actually sees here. This is what your engineering factory has over here. And then we use these features and bill of features portfolios to actually create the instances. This comes out of that ISO standard. So building on that Lego analogy, the Lego company or example, the analogy that I use for this is the master Lego builder. If you've seen the Lego, the Lego exhibits all over the world, that's the analogy that I use for the product line engineer. You need to be this Lego master, this master Lego builder. So you need to use features to express the differences across the life cycle, and of course variation management to create a full set of products that are needed by your marketplace, that portfolio of products. So the new hard skills that you need from a systems engineering perspective as a Lego master, you need to be able to understand these feature points and how to specify these feature points. You need to be able to understand the variability that's present in your products and do this variability analysis. You need to extend architecting from a single solution to architecting a product line. And another important skill is the composable design. Another integration related hard skill is looking at non-hierarchical integration. As we're continually adjusting these pieces, we might not have the traditional bottoms up integration or top down integration. We might have to do non-hierarchical integration. So these are some key hard skills that we need to master if we're in a product line environment. And some key soft skills, the ability to do this abstraction, to abstract it into these product lines, and the ability to formulate value from a life cycle perspective. You are never going to win the financial argument on the first product line, the first iteration of the product line. You're going to spend more time and more money creating a variable product line, and then you're going to reap the benefits on a life cycle consideration. So you need to be able to express value in terms of life cycle and be able to get your management to buy into that. Okay, so that's product line. If we go to system of systems engineering, our INCOSE complexity primer talks about complicated versus complex. So I leverage that definition. This is not universally accepted, but they say a complicated system is what we usually apply traditional system engineering methods to. And something like a bus can be a complicated system. It's not an easy system. It's got a lot of regulatory, safety, user comfort, driver comfort requirements. There's a lot of interacting systems, but the difference with complicated is our modeling has progressed that we can reasonably predict the emergent properties of this complicated system based on our models. Unexpected outcomes, like they say, are still possible, but usually their origin is different. So that's a complicated system. A complex system might be this turnaround here. This is I think it's Paris, but we'll say it's downtown. We'll say it's downtown Oslo. So this is a complex system, is the traffic system. It's self-organized. There's unpredictable emergence. We don't have the models to fully understand the emergent properties in advance. So it also has what we call memory. There could be a traffic jam hours ago that's even been cleared up that still causes traffic backups that come into this. And it says it has counterintuitive outcomes. So this is what we mean by complicated versus complex. And the opposite of complex isn't simple, it's decomposable. So this is the terms that we're using for this. And then from that, we leverage system of systems. There's a lot of effort going on. There's a system of systems primer that's available, but this comes from, this is what's in the handbook in section 2.4 of the handbook. And it builds on the work from Mark Meyer. He says the characteristics, you're dealing more with a system of system than a traditional system if it has both operational and managerial independence. Those are the two primary ones, but it also typically has geographic distribution, emergent behavior, evolutionary development. There's also a new ISO standard. There's a set of ISO standards that deal with system of systems. One that talks about a taxonomy from 21841, talks about virtual, collaborative, acknowledged, and directed types of systems, depending on the authority relationships primarily, and the budgetary relationships. So, but these are some typical ways that system of systems are characterized in that standard and in this primer. So when we're looking at system of systems, we look at the wave or the W model, where there's things that are done at the system of system level and some stuff that's done at the constituent level down in the red. You can still see elements of the V here, but this separates, it does a good job of separating that out. So in a system of system, the analogy I use is a conductor, where they balance the process flow between the parties. There's a lot of work that's done at the system level that the constituent system level that needs to be coordinated by the person with the baton in an orchestra. So some of the hard skills, both capabilities and requirements. We need to move into the capabilities domain as well as the requirements domain. Iterative development is key, and this new role of system integrator. Those are some key hard skills. From a soft skill, leadership is key here. Collaboration, because you don't have a lot of direct authority. It depends on the type of system, but you may not have direct authority over the constituent system. So you need to collaborate, and you need to be able to influence the constituent systems to do what's right for the system. And then I just want to wrap up with social system engineering. See, I'm getting a little bit over my time. Sorry about that. Socio-technical systems bring the human element, the social element to the forefront. We think of things like smart cities, as this is out of the INCOSE vision document. This is an example of a socio-technical systems. There's an excellent paper written by Erica Palmer from Sweden and others at the INCOSE IS that just took place. Talked about social systems engineering, but it's this reciprocal relationship between system engineering and the social sciences. How can we apply system engineering tools to social policy areas? And how can we apply social science theory for the engineering of our systems? So when we look at that, the analogy I use here is like an internet influencer. This is you're trying to influence people to do the right thing. So you need to understand the overall social objectives. You need to develop system elements that facilitate much more complex social functions. And we leverage what are called the ologies instead of the ilities. So sociology, psychology, again, a lot of these, but not all of them end in OLGY. But political science, economics, those types of things, in addition to the ilities. So our hard skills here, policy, iterative development, continuous co-design, leveraging those ologies in addition to the ilities. Soft skills, ethics. You have to have some ethical foundation to do this socio-technical systems. There needs to be empathy for the societal aspect and society and the world in general. There's a lot of conflicts that come on here, and there's a lot of politics. So you need to have skills in conflict management and recognizing and dealing with politics when you're doing socio-technical systems. So with that, just want to quickly wrap up. We talked about what do we mean by traditional system engineering, and we talked about how we can transition from Greenfield traditional system engineering using additional hard and soft skills. So with that, remember the last plug is all those soft skills I talked about. If you want to get better at those, you're going to have to jump in the pool. You're going to have to be like that dog on the right and jump in the pool to see if you can really swim. So with that, I will turn it over for questions.
Hey, super. Thank you very much, Dave. And once again, let's thank Dave with the reactions button and recognize his excellent presentation. All right, Dave, you've had a few questions pop in, and then we'll maybe just limit it to the top few. Alexander has entered a question about brownfield systems engineering. And an article that he's read about institutional memory and reverse smuggling. And he's suggesting that almost all systems engineering now probably is more brownfield. He mentioned something called an M model, M as in mother. Did you want to comment on that?
Yeah, there is a correction. It's an N model. I mean, it's a modified V model. Yeah, but it's brilliant. It's brilliant. We are discussing now for 15 minutes.
Okay, thank you, Alexander. Never mind. Then he was just complimenting on your model from Sysnovation, Dave. Another one is wondering, is the N model really an innovation, or how would you, if you were asked to defend it in some way, Dave, what might you say? And that's I won't say who asked that question. You can read it in the chat later.
Okay. All right. Well, for Alex's question, thank you, Alex, for the question. So I think you are correct that a lot of systems, if you look at innovation literature, we talk about, radical, and if you just, one way you can partition innovations is radical innovations and incremental innovations, right? And radical innovations are the ones that get all the press, right? That's the Steve Jobs of the world, where they're, oh, we're introducing something new to the world. It's, you know, the subject of a lot of excitement in the press. But they say that incremental innovation, sometimes called nuts and bolts innovation, is where all the money is. Okay, all the press is in the radical innovations, and you only hear about the ones that are successful. You don't hear about the 60% that fail, right? But you hear about, then everybody thinks that that's the way to go, is with the radical innovation. But this incremental or nuts and bolts innovation is very important. And I agree that a significant number of innovations right now are brownfield, or what we call legacy system developments, where you start with something new. So my point in introducing this is that, again, as excellent as this handbook is, says the lead editor, we need to make sure that people understand that you don't always just start with a clean sheet of paper. You can't always just go out there and find out who your stakeholders are from a clean sheet. You've got to understand the legacy stakeholders and then build in the new stakeholders as well. So I would agree. And I think your comment on institutional memory and reverse smuggling is very good as well too. That's reverse engineering is one of the ways that we do reconstruction. And to Marcus's question about the reconstruction, I will leave it to you to judge if it's innovative or not. What I think people could argue, you should be doing all those things on the left-hand side of the V already. I think the benefit that it provides is by making them be explicit with the site survey and the reconstruction activities, it makes it be something that you don't forget. Sometimes we forget to do these things, and I think it helps with that, but I will leave others judge whether it's innovative or not.
Okay, well, it appears you have covered all of the questions, so I'm going to say thank you again, Dave, and revert to Tom, who will close the session for us. And thanks to all of our speakers who have really made this a very worthwhile afternoon.
Okay, I think that's over to me then. So let me just share my screen. Thank you, Dave. That was really excellent. So we are getting to our last point on the agenda for today. There's actually a number of things under that one. So let me start with just telling you a little bit about INCOSE. It would be interesting actually to know how many of the participants are members of INCOSE. So I don't know, Ricky, would that be possible to do a poll as we talk, maybe?
Yes, I can launch the poll here, so I don't know if it. Sorry, let's see that. Yes, it should be now running. All right, very good. So we can keep that. Well, I'll put it back after the while here. Okay. What happened now? Okay, I got something, a bit of conflict with the window. Yeah, I know, but this is it preventing you then going on when the poll is ongoing. I don't know how it works with the Zoom. Yeah. So anyway, there seems to be a few who are not members, so maybe it's good just to give a little short overview of INCOSE. INCOSE changed its vision 2016, so we're all really here to talk about how we can make a better world through a systems approach. And doing this, of course, we are doing things like we do today. We are sharing experiences. We are talking about the promotion, advancing of the systems engineering and system approaches. So looking at the bottom here, there are a number of elements to this. Today, starting from the right, we do a seminar online this time, but we of course also have the annual symposiums and international workshops, etc., where we actually can meet physically as well, pandemics allowing, that is. We have a lot of active and very interesting working groups. So I think if you have any interest in any area in systems engineering, go and check out the working groups, and maybe you can join. You can join as passive or active members. The more my own experience is, the more you put into those, the more you get back, of course. And those are divided into certain application domains, industry branches, and also enablers, where we talk about the processes and methods and tools, etc.
And of course, the major part and the major asset of INCOSE is its 18,000 members, split up in or grouped into 70 plus chapters. Also, there's a corporate advisory board comprising more than 120 companies and universities these days. So a good forum to actually drive the needs and directions for INCOSE for the future. We already touched today about how you can develop your own professional skills. So there is the certification, the new competence frameworks, and a lot of webinars to support this. So check that out. And also as a member, of course, you get access to a lot of products. Just to mention, of course, you can't miss Dave's, and Cecilia has been heavily engaged in the Systems Engineering Handbook. And there are a number of good guides. There's the journal, the newsletter, the insight that you get automatically as a member. And there are other things like the tools database that you can explore. So I think, as a member, you can get access to a lot of assets here that helps you to promote INCOSE. And of course, INCOSE is a voluntary organization. So we're all driven by, I guess, our own interest in this area. So is the leadership. So I thought I'll take this opportunity because some of you who are members may already know that I'm one of the presidents-elects for the upcoming. But also, I think we have Ralph online. Ralph, are you there?
Yes, I'm here. Can you hear me?
Yeah, can we see you too?
Perfect, perfect.
Very good. Because I thought it would be good just for everyone here just to actually see that we are live and that we actually are real bodies behind the words. So Ralph, you may want to say what we wanted to promote.
Yes. So yes, good afternoon, everybody. So for those of you who are INCOSE members, you may be perfectly aware that every 4 years, basically, there's an opportunity for a non-US candidate to be elected as president-elect and president. So that means a 4-year leadership role for the organization. And this year, again, is one of those opportunities. And Tom Strandberg and myself, we are in friendly competition this time to be elected for the next president-elect and president of INCOSE. And I think we are both super enthusiastic about this, being long-term, let's say, engaged members of the organization. As you can read here, what we don't want to do a promotion here of ourselves. You can go to the website, you see the webinar, you see our bios and our vision for INCOSE. For those of you who are interested in it, those of you who should be interested are the members. And we really want you, let's say, to promote the fact, please vote, so that most of you are from also the European community. We need to make sure that that this is really also appreciated and recognized outside of the United States. And please vote. Tom and I, let's say, will be the ones waiting for your vote, and then being also the, let's say, the reliable and enthusiastic and engaged leaders for you if elected for the upcoming years. Thank you for that.
Indeed. So sorry for stealing a little bit of time, but I thought it's a good connection, and in particular, as any one of us will be dealing and taking your interest into the leadership in the future. All right. So I think we just a final point here was to have an overview of what's happening. Here's a list of the events, and you can read that. You can find most of this information on the different sites, the chapter sites. We could just point out that the time is also ripe now for getting together and write papers or propose panels or tours for the next year's International Accounts Symposium in Detroit. So that's due on the November 14th. The MEA workshop also coming up in October, so it will be a virtual one. And then you have a number of interesting local events, even though, I mean, these days with the virtual online experience you can take. You can be anywhere in the world, and I think we have actually had quite a good representation already today from outside the Nordic region. So I would like to thank all the presenters really much, and then that's on behalf of all the NoSE committee, and we hope to see you next year. Before I close, anybody who wants to say something, you can unmute now, or if you want to announce something. Cecilia, Ricky, any last words from your side?
Yeah, thanks, Tom. We have been recording this whole session, so we will provide you at least the link to the recording to you, so it's possible to see these presentations again. So, and I think we are also providing links to the presentation materials. So that's what we are planning of. So thank you on my behalf. So it has been a pleasure, and I think the previous formats have been nice, but I think that this has also been a good way to go, because we can see friends from different countries. So it's not just people from one country, but I think that it might be a good thing also to get back to the traditional way of doing NoSE tour in future.
Yeah, right. Have you seen the poll?
Yes, yeah, the poll says we have now 50 answers, and 64% are members, 12% used to be members but are no longer, and 24% haven't been members of INCOSE. So quite good that we have also members or not members that might be thinking of joining. So hopefully we can get you to see the value of being member of INCOSE.
Okay. Excellent. Well, there's hopefully this has at least inspired you, to those who are not members, to become members, because I think this is a great community, and we do need more systems thinking, acting, and management for a better future. So with that, I think we stop. I saw there was a question why the voting for me, but then I think we'll go beyond the time allocated here. So, but I think you can read in, and then both Ralph and I are, of course, very open to have any exchanges. All right. We are closing a bit ahead of time, but I think that's a good sign that we are effective, right? And I'd like to thank everyone and see you soon again. Thanks.
Thank you very much. Bye-bye.
Bye-bye.
Thank you. Bye-bye.